Welcome, welcome. All right, everyone, we are going to get started. Good afternoon. My name is Harriet Bredel. I am the Exec Director here at the Keck Institute for Space Studies, and it is my absolute pleasure to welcome you here to Caltech. It is fantastic to hear so many British accents on Caltech's campus here today. Thank you so much to everyone in the British delegation who's joined us. We have a fantastic lineup of talks and panel discussions to set us ahead for this afternoon. So thank you very much, everyone who has joined us, whether you've come from the other side of campus or the other side of the world. I'm going to speak very briefly because I want to hear from our fantastic speakers here today. But we are here today to celebrate UK-US space collaboration, and it's been fantastic to see the number of missions, collaborations, research ideas that have already been developed, underway, and have happened so far. And so I just want to say thank you to everyone for the collaboration that we're going to be celebrating today, but also the opportunities we're going to have in the future to continue that collaboration going forward as well. We have a jam-packed agenda this afternoon, and so I'm really excited to keep to time as best possible. I'm going to be doing my best British diplomacy to keep us moving through our fantastic lineup. To kick us off, we've got some wonderful opening remarks from a number of esteemed colleagues, so I just want to say again a huge thanks and welcome to everyone who is joining us. To begin, I would like to hand over to His Majesty's Consul General, Paul Rennie, OBE. So Paul, over to you. Thank you.
Good afternoon, everyone. I promise to keep these remarks very brief. Sadly, in 25 years of diplomacy, no one's ever said, "Great speech, Paul, I wish it were longer." So what I really just wanted to do is, first and foremost, say it's a huge, huge pleasure and a privilege for me as Britain's Consul General here in Los Angeles to open this Greater Together UK-US Space Symposium. Obviously, partnering with the Keck Institute for Space Studies, Caltech, JPL, three institutions that are just absolutely dynamos when it comes to our journey through space and space science and research is an enormous privilege for us, and a huge thank you to them for all of their work in making it happen today, and also to my team as well for bringing us together. Of course, the UK hasn't come empty-handed to these conversations, and I'm going to have to read this list because it's a long list, because we have with us today the UK Space Agency, University College London, University of Leicester and Space Park Leicester, University of Warwick, Bangor University, UK Astronomy Tech Centre, University of Sussex, RAL Space, Open University, Imperial College London, University of South Wales and the University of Oxford. When Paul Revere said the British are coming, this is what he meant. So it's fantastic to have you all here, great British institutions and great leaders in their fields as well. And of course, the quip about Paul Revere, it is the 250th anniversary of America. And so I'm quite pleased things are going much, much better today than they were for us back then. I'm always conscious, as all of you involved in the space journey will appreciate, every time I hear the American national anthem talking about the rocket's red glare, those were, of course, British rockets. And I say nothing about whether JPL might have made them better or not. But I'm glad that we have this kind of partnership. We're glad we have this kind of relationship together. And I think if you imagine back 250 years to how it was and think how it might even be by 2076, never mind another 250 years in the future, it's incredibly telling how fast things are changing, how fast things are moving. And for me, this symposium today is really a way to think about and imagine that partnership going forward, and how science and the partnerships in science are really at the core of everything we can achieve together. In May this year, as part of the Greater Together programme, we will be welcoming what we think is probably the largest trade delegation we've ever brought to America, here in Los Angeles. And I think bringing that trade delegation here is an incredibly important reminder about how much the private sector and the public sector now go hand in hand in the science journey and hand in hand in the space and the research journey. And I'm very much looking forward today to hearing more about that from the US perspective and from our incredible colleagues from the UK sharing their perspectives as well. Otherwise, there's no more for me to say other than let's have a wonderful, wonderful time at the symposium. And I have to say, just think, you can imagine, when I began this conversation, I wanted to start with space, but I couldn't figure out what the gag was after that. But you'll have much more fun than that later on today. Thank you, everyone, for a wonderful afternoon.
Fantastic. Thank you, Paul. Next up, I'm thrilled to welcome up Stephanie Ashmore, who's the Director for the Americas Science and Technology Network at the British Embassy. Thank you.
Thanks, everyone, and good afternoon. I'm Stephanie Ashmore. I'm the Director of the UK Science and Technology Network in the Americas, based in Washington, D.C. So it's been a great privilege to be here in LA, the global home of space innovation, for today's symposium. And the delegation have had a really great couple of days exploring the LA space ecosystem. So our network has 17 offices across the US, and we work on a really broad range of areas, including AI and quantum, synthetic biology, fusion energy, and of course, space science. We work very closely with the UK's Space Agency and the UK Space Research Enterprise to catalyse exactly this kind of transatlantic collaboration that we are celebrating today. Space has always been a really important pillar of the UK-US partnership on science, and it is one of our most forward-looking. In the 1960s, Ariel 1 made the UK the world's third spacefaring nation. It was built and launched with NASA and became a landmark in international space cooperation. That first joint satellite set the tone for 6 decades of shared discovery, and the legacy of that is alive and well. UK engineers led the MIRI instrument and the James Webb Space Telescope, revealing the universe in unprecedented clarity. UK teams have also contributed to Solar Orbiter, and most recently, IMAP, each pairing British ingenuity with US mission platforms to deliver global science. It's a powerful formula. British instrumentation and ideas flying on American rockets and spacecraft. We have also aligned our rules and norms for exploration. The UK was among the original signatories of the Artemis Accords in 2020, committing to transparency, interoperability, the release of scientific data, and the peaceful use of outer space. These principles help every mission succeed. Politically and economically, both our governments have renewed their focus on the space sector. The UK Space Agency has invested millions of dollars over recent years to accelerate our bilateral partnership in space science. The US-UK Technology Prosperity Deal signed last year also provides a framework for partnership between NASA and UKSA to develop new space-focused AI capabilities. So as Paul said, today's symposium is sponsored by the UK's Greater Together campaign, and that was launched to celebrate the importance of the special relationship as America approaches its 250th anniversary. It will showcase how our countries invest in each other's futures and how collaboration turns bold thinking into real-world breakthroughs. From Ariel 1 to Artemis, from pioneering instruments to shared operations, our story in space proves that when British and American ambition and expertise come together, we make our peoples safer and more prosperous back on Earth. So thank you very much for being here and for the ideas and the partnerships and the missions that will be initiated in this room today. Thank you very much.
Fantastic. Thank you so much, Stephanie. All right. Fantastic. Next up, we have John Eiler from Caltech. Thank you.
Thanks very much, Harriet, and thanks all of you for being here. I noticed I am the only person from your host institution to welcome you, so I offer you the biggest possible welcome. I'm also the only non-British citizen, I think, offering introductory comments, so in my defense, I'm also the largest and baldest, so maybe that makes up for the rest. I'm a professor of geology and isotope geochemistry. Also, I'm a chairman of the Division of Geological and Planetary Sciences, and I have the pleasure of serving on the supervisory committee for KISS, the Keck Institute, and in that capacity, I get to work with Mike Watkins, its new director, and the indomitable Harriet Brettel, who is our leader in all respects. So thank you very much, Harriet, and the organization for organizing this event. So The subject of our meeting, the collaboration between space scientists and engineers and explorers in the US and the UK, it's something that has tremendous bones and a great deal of history to it in several different respects. And I think this is really essential because relationships are built by doing things together, and we have done great things together. Hubble, Webb, Curiosity, Perseverance, LIGO, Juno, Cassini, and on and on and on. We have done an enormous amount together of tremendous ambition and creativity, and we will continue to do that. Out of this discussion will come the things that people discuss a decade from now and add to that list. I think it's also important that we share very deep scholarly genealogical connections. So for my own personal story, I spent formative time at the University of Edinburgh as a graduate student working on what was then one of the most advanced analytical laboratories in the world, learning to do totally novel measurements of isotopic composition in Martian meteorites and other sorts of materials. Every single class I have taught at Caltech over 30 years has been grounded in the founding concepts that came out of a collection of Scottish lairds and Cavendish lab sorcerers who invented the basic platforms of the instruments that I've built my career on. Everyone you can imagine, Rutherford, Thomson, Soddy, Aston, all of them. Even Margaret Todd, who invented the name of my field, isotope geochemistry. So Margaret Todd was a medical educator and author in early 20th century Britain, and she invented the word isotope at a dinner party, as it was. So welcome to all of you, and I have great hopes for what's about to happen. A few words about your host institution. Caltech is, like a lot of great universities all around the world, all of your homes, it is unique in two ways. One is we are not only in association with JPL, JPL and we are joined at the hip. We are outgrowths of each other. And that the fact that we have grown up together for over 90 years, this is a very deep thing. And it means that the science and engineering of campus and the science and engineering of the lab and their ability to work together on the most ambitious projects, it's something that it really has a unique character. The second thing is that the institution goes beyond collaborative, beyond interdisciplinary. Once people walk inside the four sidewalks, which you are now in, you are part of a family. And the family has no internal divisions. People wander from department to department, subject to subject, level of seniority up and down. The idea of working together seamlessly across seeming divides comes very natural to us. And KISS, I would say, is the ultimate manifestation of that. It is a kind of summer camp for nerds where you come together. Where did you make all your best friends? Summer camp. So come to KISS, make new best friends, and I hope we all have a wonderful day here. Thanks.
Fantastic. Thank you so much, John. All right, next up, we have another Brit and honorary American, Georgina Good. Thank you.
Thank you, and thank you, John, for that perfect description of our close ties with Caltech and all the wonderful work we have done together over the last 90 years. We're finally in our year of 90th celebration. So, Georgina Good, I am the Deputy Director of Strategy and Formulation at JPL. I firstly wanted to say thank you to those in the room that attended the lab this morning with the tour and the workshop sessions on planetary and science, etc. Really rich discussion, and I understand it's the second delegation of the UKSA and UK academia onto lab over the last couple of years, which is just a testament of the rich partnership that we have. And the conversation was fascinating, compelling, and really future focused on some of the collaborations we can potentially look at as we move forwards. Sessions like those are just such a great way to create space for a meeting of expert minds and rich experiences and perspectives. So thank you to all of you. You know, our motto at JPL is dare mighty things. No one person alone can send rovers to Mars, can send spacecraft to Jovian moons, can address Earth's changing climate or uncover the many mysteries of the universe through the most precise instrumentation to ever be invented. And it takes diverse teams and immense collaboration, which we've touched on already in some of these introductory remarks, to accomplish what many think is impossible. And that's why sessions such as this morning's and this afternoon's cross-sharing with all of you today and our expert panels are so very important. For decades, NASA, JPL have had a very rich, diverse partnership with the UK, with UK academia, and this afternoon we'll celebrate just that. Many of our accomplishments, which we've touched on, I know we'll be discussing this afternoon, an ongoing success based upon the thriving partnerships that we have. The relationship we have with the UK and the close working ties that we have with many of you in this room remain the basis for how innovation flourishes, technology advances, and how we accelerate scientific findings, how we overcome obstacles and achieve our mutual goals. And certainly at this particular juncture of space, US space history, I will say, global space history, where we're moving faster than ever in establishing an enduring human presence in space, increasing the rate of world-changing scientific discovery, helping strengthen the orbital economy, there really cannot be enough of what we're doing today. So I am personally, I'm going to keep it very short because we want to get to the meat of this afternoon, so I'm personally very excited to be here with you all today. It's a privilege, and I'm very much looking forward to the panels that will follow. So thank you very much. Thank you.
Fantastic. Thank you so much, Georgina. All right, our final opening remarks are from Adam Amara from the UK Space Agency. Adam, over to you. Fantastic. Round of applause for Adam as he makes his way up to the stage. Thank you.
Sorry, I didn't position myself in the right place. Thank you, everybody. It's been wonderful to be back here again. As we said earlier, this is the second delegation to come down to JPL with a set of UK academics. And what that allows us to do is continue to build momentum. And this momentum has been growing for a number of years as the UK has formalized sort of the ways that we want to work with partners across space in a bilateral program. And what we had today was a very lively discussion at JPL. I think we managed to cover a lot of grounds. What's really interesting is that these are conversations that you can only have in person that don't quite materialize even online, no matter how good your connection is. You can never quite get under the belly of some of the key issues. The space sector in the UK has changed a lot over the last year, and we continue to go through a significant amount of change. The Space Agency is merging into its broader government department. This has caused widespread anxiety, as often transformations do. But in my opinion, this is a very good move for the UK. It allows us to be more strategic. It allows us to define our strategy better across all of government. What I'm particularly excited about is that the mandate that's been given to the Space Agency is very clear. It has two parts: to cohere space across all of government under a one government approach. So that's great. As soon as you get coherence across a broad space sector, that's a really excellent thing in terms of cohesion and ability to deliver. But the second part of the mandate is to deliver world-class innovation and science in partnership with the sector and internationally. And I think what we're doing here, it aligns exactly perfectly with that. So as the new Space Agency stands up on April 1st, and for the first time in a long time, we'll have a new agency, a very clear mandate, a very enthusiastic minister, it turns out, and also our budget has now been set for the next 4 years. So we have more clarity to plan and support the collaborations that are emerging here than we have done for a very long time. So I'm very much looking forward to the panel discussions to see how we can support the projects as they emerge. Thank you very much.
Fantastic. Thank you so much, Adam. All right, super. So I'll put this down. Fantastic. So it is my distinct pleasure to welcome McGann Christian to the stage. McGann is a UK reserve astronaut and senior exploration manager at the UK Space Agency. She has a fantastic career story to date, and I can't wait to hear all about it. So without further ado, I'm going to just transfer our slides over. And with that, we'll hear from McGann. Thank you.
Thank you very much. Thank you. What an honor to be here. Keynote at Caltech. I think, the imposter syndrome is strong. But I think when you have astronaut in your title, you kind of get used to being in a room full of people that are more intelligent than you. I'm quite happy to go to space, but there's no way I could get somebody to space or get an instrument to space. So that's all about you. I don't want to take up too much of your time today, but I'm here to break the ice a little bit by telling you my story, how I ended up where I am today. And I call that From Antarctica to Space, and you'll see why in a moment. So for those of you from the UK, you will realize that my accent is not exactly British. I was born in Kent, but when I was 5 years old, my family moved to Australia, and I grew up in a city called Wollongong. I went to the University of New South Wales in Sydney, and then after my PhD, I moved to Italy, to Bologna, to the National Research Council, and from there, the last couple of years, I moved back to the UK. So that's 3 of my citizenships. I actually have a 4th because my parents are New Zealanders, so I'm one of those weird people with multiple passports. Just a bit of my background. So I did my undergrad in industrial chemistry, engineering and industrial chemistry. After that, I did a PhD in industrial chemistry in the Faculty of Engineering on core shell borohydrides for reversible hydrogen storage, basically nanomaterials for fuel cell vehicles. And from there, I was looking for some international experience. I had some international passports. And so I was looking for a postdoc in Europe. And I did find one, which was kind of a follow-on from my PhD in France. But as often happens, the funding fell through. And I ended up finding another one in Bologna at the National Research Council in a subject that I really knew nothing about. A material called graphene. Perhaps you've heard of it by now. I hadn't heard much about it, but I read a lot about it, got more and more interesting the more I read, and then having done a series of interviews, I ended up moving to Italy. I didn't speak Italian. I'd been to Italy maybe when I was 3 years old, but took that leap of faith for what was supposed to be a 1 to 2 year postdoc and ended up staying there for 9 years. So clearly, I did enjoy it. Mostly, I was working on graphene for various sort of energy applications, but there was one space application that appeared. I was working on using this material I was making for coatings in cooling devices in satellites, for loop heat pipes. And so, of course, to be able to test that these can work one day in satellites, we had to test them in conditions of weightlessness on parabolic flight. And so I got to do my first parabolic flight back in, I think it was about 2017. And it was great fun. I really, really enjoyed it. Unfortunately, I went back a second time for another parabolic flight a couple of years later, just when I was applying to become an astronaut. And I found out why it was called the Vomit Comet. Yeah. It's so for those of you not familiar, it does this maneuver where it climbs up very, very steeply, then floats over the top of a parabola, and then comes down steeply and comes out of that parabola. At the beginning, you have 20 seconds of 2G. In the middle, you have 22 seconds of weightlessness, and then you have another 20 seconds of 2G, and it does this 31 times. So I was quite worried when this came along later, and I spoke to the doctor on board, and he said, actually, you know what? That's quite different to the mechanism that astronauts have for getting space sickness, so you're probably okay, and thank goodness for that. But that's later in the story. So I've always been a curious sort of person. I think we all are when we're children. I think everybody in this room remains curious. And when I was about 12 years old, I went to the International Antarctic Centre in Christchurch in New Zealand. And that stuck with me as this really fascinating place. And I thought, maybe one day I'll make a lot of money and I'll get to go on a cruise to Antarctica. Well, I haven't made a lot of money, but spoiler alert, I have been to Antarctica. I also love a challenge, which is probably why I ended up pursuing a career in research, to be fair. And I love adventure, adventure sports of all kinds, climbing and whitewater rafting, scuba diving, cross-country skiing, that sort of things. So for all these reasons, when the opportunity came up to go to Antarctica while I was working at the National Research Council of Italy, it seemed like a no-brainer. But actually, I got that email and I said, you know what? There's no way they'll accept someone like me. I'm a materials scientist. They're looking for somebody to do atmospheric physics and meteorology. I knew what meteorology was, but didn't really have a good idea of what atmospheric physics was. So I kind of let that one slide. But then it came up again a year later. And I thought, yeah, I'm just going to send them an email, see if they'll accept an application from someone like me. And turns out they did. They said, yeah, come and have a chat. That chat was an interview, and next thing you know, I'm headed to training and then on my way to a continent of absolute records. It's the most isolated, the coldest, the most arid. It has the highest average height above sea level, has the highest wind speed on the coast, though not where I was at Concordia, and at the same time as being a desert, it's the largest freshwater reserve on the planet. And that's the patch of my crew, which was the 15th winter over crew at Concordia Station, which is located right in the middle of the Eastern Antarctic Plateau. And you get there, first of all, by flying a military plane, C-130, from Christchurch in New Zealand, right next to the International Antarctic Centre that I had been to when I was 12 years old, to MIRI Station on the coast. And then from there, take a small plane, a Basler, DC-3 to Concordia Station. So that first flight is about 7 or 8 hours, and the second one is another 4 hours. So by the time that you've gone there from Italy, you're pretty tired. But the reason that particular location was chosen was for a project called EPICA, European Project for Ice Coring in Antarctica. They drilled an ice core that was 3,270 meters long, cut it into slices, and analyzed the gas bubbles that were inside each of those slices, correlated the depth of that slice with the period in history, and that's where we get this really famous graphic of the amount of carbon dioxide and methane that there has been in the atmosphere going back 800,000 years, and how much that has increased in the past 150 years due to human activity. So it was really quite special to be in a place where we had that true confirmation of what we knew was happening. And there's a project now called Beyond Epica, which is going back 1.5 million years. And the second time I went to Antarctica, yes, I got to go again, I actually got to visit the site of that, which is about 45 kilometers away from Concordia Station. This is what the base looks like. It's made up of 2 towers, a quiet tower and a noisy tower. And there are all sorts of different sciences that we do there. You can see them listed there. As I said, I was in charge of atmospheric physics and meteorology. But there are also some interesting conditions that you have to face when you're there. We had 100 days when the sun didn't set and 100 days when the sun didn't rise. So that was pretty tough on mind and body. The temperature got down to minus 104 degrees Celsius wind chill. Not exactly sure what that is in Fahrenheit, but it's really, really, really cold. We had that the humidity was really low as well. It is at those temperatures. There's not much you can do about it. Also, low atmospheric pressure, because we're at an altitude of 3,233 meters. The air is thinner at the poles, so that's more like being at 4,000 meters. So you can imagine all these things combining make it really, really tough on the human body and consequently on the mind as well. The kind of tasks that I was doing, I was in charge of a number of projects. I'll just highlight a couple. The Baseline Surface Radiation Network, which is all about gathering basically albedo data from many, many different places around the globe, but in particular getting baselines there at Concordia Station and around Antarctica. And some of these instruments are on this 45-meter high radio tower, which interestingly is called the American Tower, that I had to go out and basically clean the ice and snow off every week. I'd climb up there. It was about 1 kilometer away from the base, so you have to walk out, dig the snow up to get the harness out from under the snow, put your harness on, climb up, clean the instruments, come back down again. And all this under the tough conditions and the high altitude and so on. So this was probably the toughest part of the week, but it was also the best part of the week. Because my colleague and I that would go there, we would use that time to let our eyes adjust to the darkness. We would take our headlamps off and just look up at the stars. And it was incredible. I mean, you know something about this here in California, that's for sure. I've seen an amazing night sky here. But in Antarctica, in the polar night, it is something else. There were so many shooting stars, and the stars were so bright. If I looked down, and it was a moonless day, I could see my shadow in the light of the Milky Way. It was phenomenal. And you can see why that would be inspiring for somebody like me. But most of the time, I was just walking around with basically a hairdryer and a paintbrush to remove any snow and ice buildup from just about anything there was. I also launched the weather balloon every day. Weather balloons are launched all around the world at exactly the same time. There's a message to my husband on this balloon because, that's the only way you can get messages out of Antarctica, by sending weather balloons. It was his birthday. No, this is just to show that, we take routine weather observations, which are clearly used for us, but also for weather predictions and also for putting into weather models. Usually it's not that windy, but some days the balloon did nearly carry me away. And there were some other projects, but one I just wanted to mention was the fact that Concordia Station is also known as White Mars. It's the closest thing we have on Earth to what it would be like to go on a mission to Mars, the isolation, the confined environment and the extreme conditions. And so the European Space Agency sends a research doctor there to do all kinds of tests on us. They take every kind of sample imaginable every month. And they test them to see what happens to the human body under those conditions. We had many, many questionnaires to fill in as well to see what happens to your psychology during that time. And a particularly fun one was that they taught us how to dock the Soyuz onto the International Space Station using this simulator. And then we they gave us increasingly difficult exams, and they split us into groups, and we had to do challenges again at kind of defined intervals throughout the year to see whether we remembered how to do it over that time. Because if you think about it, if you're going to go land on Mars, sure, it's the people on ground that are doing it, but I mean, Mars is a long way away. We all know that. So humans have to have something to do with it. They have to know how to operate it. They have to know still how to operate it by the time they get there after 6 to 9 months. So what's the kind of training regime that needs to be in place during a mission? So I learned a lot about myself while I was in Antarctica. I was worried before I went there that I wasn't going to be able to pick up these skills that I needed in a completely different field. There was lots of electronics and programming that I hadn't done before, but I loved that steep learning curve. And I also loved being the custodian of other people's experiments. People would put their life's work into designing these experiments, but couldn't be there to be the hands themselves. And so I thought, well, I want to keep doing this. And so when, for the first time in 13 years, the European Space Agency opened up applications for astronauts, clearly I applied. And unfortunately, also 22,500 other people applied. So we had to go through this rather long 18-month selections process, sending in a CV motivation letter. Then there were computer-based testing on things like physics, maths, logic, memory, hand-eye coordination. Then we had a series of psychological tests, teamwork exercises, communication exercises in pairs. We had a full week of medical testing. Really everything. Yep, they did everything. Then we had a panel interview, which wasn't, everybody does panel interviews. It's part of our working life. But this one was probably, for me, the most challenging part of the whole process, because any time that you were in your comfort zone, they took you right out of it. And then finally, there was an interview with the Director General of the European Space Agency so that he could make his final decision on who was going to be selected. And in November 2022, that class was announced. And I was I was shocked every single time that I got the call to go to the next round that I was going to be there. And so you can imagine how I felt when I was on this stage in Paris being announced in the astronaut class of 2022, along with two other colleagues from the UK, Rosemary Coogan and John McFall. Rosemary is our career astronaut. John is the world's first astronaut with a disability. And then there's me, reserve astronaut. So, you know, I was honored and excited to be there. Also a little bit disappointed because I wasn't selected as a career astronaut. That meant that I didn't go straight to be employed by ESA. I didn't go straight into training. I didn't quite know what was coming. We still don't really know what's coming, but interestingly enough, the first two people from my class to fly have been Marcus from Sweden and Sławomir from Poland, who are both reserves. So they've both had missions to the ISS already. Who knows what the future holds? So in the meantime, what is all this for? Well, this is the master plan of the Human and Robotic Exploration Division of the European Space Agency. You know it well. We have the ISS, we have the Artemis missions going back to the moon, and we have our beloved Rosalind Franklin rover, which will be heading to Mars in 2028. And sometime later, it was announced that our class of reserves would also get to go through basic training. And I've done 2/3 of my basic training so far. Well, 2/3 of some of it. So just showing you some photos. We had a lot of engineering modules and understanding the International Space Station, and a lot of that is done in VR, which really gives you a good feel for how it's all done. We've had scientific modules, biology, in the classroom, but also in the lab. We got to handle some of the instruments that were on Artemis 1, which was extremely exciting. One of my favorite classes were the medical classes. We did a lot of the theory in VR, and the people who had been through medicine at university before were pretty jealous of us getting to do VR in this, because it makes things so much easier to just kind of, instead of memorizing things on a page in a textbook, we could actually, you know, reach out and grab bones and increase the size of them and just see what it was all about. And then, of course, we got to do some practical training as well. We also did things like photography, because, you know, you actually do have to be pretty good at photography on the International Space Station, strangely enough. We did media training and social media training, presentation skills. Actually, one of the first things we did was human behavior and performance training. So understanding how to work well in a team, how to be a good leader, but also how to be a good follower, how to have good cross-cultural awareness. And one of the really cool things about this class was that we did it with some of the astronauts from India as well. We've done survival training, sea survival training. We've done firefighting. We've spent a lot of time underwater in the neutral buoyancy facility, because that's the best way that we have to simulate spending long periods in weightlessness. And we've done some more of those parabolic flights. And I've now done 7, and I've worked out how not to get sick. Yes. So I was very happy when I was doing these particular flights, because I was not sick. I was having a great time. I was learning new skills, and these are exactly the kind of skills that one day, hopefully, I will get to use on the International Space Station, or indeed one of the commercial space stations in the future. And of course, one of the other important things is to keep fit. So we spent a lot of time in the gym too, and that's just a bit of a girl power photo, because there is almost half our class are women, which is quite exciting. But I don't spend all my time in training. I'm also at the UK Space Agency in the exploration team, and we need to get to the proper science, so I won't go too much into detail here, but I just wanted to highlight a few of the little things that I do that are in collaboration with you. So one of the things that I'm responsible for is working on our post-ISS strategy. How do we continue to do the kind of science and research that we do now on the ISS with commercial space stations in the future? And that depends on the NASA CLD program. We also support UK technologies that can one day benefit human exploration. So this is another parabolic flight, where I was testing an exercise device for astronauts that was built by a company in London. And they're working on a contract with the European Space Agency to perhaps have their exercise device on the Gateway. together, we collaborate to unlock future missions, and we've been talking about this today, in fact. But for example, I lead the exploration side of the ENDURE program, which is radioisotope power systems for future deep space missions. The first radioisotope heating units will be on the Rosalind Franklin mission in 2028. You can see a small one there, and eventually on Argonaut, as you can see this, which is the European large lander. And then another side is something that is to benefit for all of us, and that's the commercial side of things. Commercial benefits for all of us. So it's in our best interest to stimulate this kind of economy, and part of that is in-orbit manufacturing of both advanced materials and pharmaceuticals. And there's the 3D bioprinting side of this as well. I mean, one day we could be printing the organs that we have in our transplant lists instead of having to take them and wait for very, very long periods of time. So it's hugely exciting. I just feel so privileged to be able to do both of these things, to train to hopefully one day be an astronaut, but also to kind of help to prepare the future of exploration. Thank you very much.
All right, fantastic. I think we might have time for one question from the audience. If anyone has a burning question for Megan, please raise your hand and we will get a mic to you. All right, Zach, we've got someone all the way at the back. Thank you. Keep your hand raised so Zach can find you. Thank you so much.
Hi, Alicia Jota, UCLA. So what's your trick for the vomit comet? How do you survive it?
Medication.
Oh, okay.
You have to find the medication that works for you and the correct dosage. But also there are some kind of breathing techniques that you can use. You also have to make sure that you eat properly. So don't eat too much, don't eat too little, don't be too tired. Don't be too cold, and all of these things combined means that you can have a pretty good flight.
Thanks. Fantastic. All right, one more round of applause for Megan. Thank you, Megan.
Thank you.
All right, fantastic. So I'm going to move us back to our main deck. Okay, fantastic. So it's now time for our panel, and it's my distinct pleasure to invite Irina Chatia, who is going to join us to introduce our panelists here today. So Irina, over to you. Thank you so much.
Thank you, Harriet. Good evening, everyone. It is a great honor to introduce Charles Alachi, Professor Emeritus of Electrical Engineering and Planetary Science at the California Institute of Technology and former director of the NASA Jet Propulsion Laboratory. Professor Alachi led the Jet Propulsion Laboratory for more than 15 years, making him one of its longest-serving directors at JPL. During that time, he oversaw the extraordinary period of discovery, with involvement in more than 20 missions spanning Earth science, planetary exploration, and astrophysics, including landmark missions to Mars, Saturn, Jupiter, and beyond. Notably, 3 Mars rovers, Spirit, Opportunity, and Curiosity, successfully landed on the Martian surface under his leadership, representing a rare and defining period of sustained robotic exploration overseen by a single director. Equally important, Professor Alachi made international collaboration a core strategic pillar of JPL's work. Under his leadership, the laboratory moved beyond coordination to true co-development with partners across Europe, the United Kingdom, France, Germany, and India. In 2006, Professor Alachi was awarded Royal Society of London Massey Award. These collaborations delivered globally significant advances in planetary science, heliophysics, climate and gravity science, sea level monitoring, and Earth observation, and helped establish enduring models for shared governance, shared engineering responsibility, and shared scientific return. Please join me in welcoming our moderator for the panel, Professor Charles Alachi. and I will introduce other panelists. So joining Professor Alachi this evening is an outstanding panel of scientists from the United States and the United Kingdom, whose work spans planetary science, heliophysics, geobiology, and space instrumentation. So first, Woody Fisher, Jean-Loup Chamou Professor of Geobiology at the California Institute of Technology. Professor Fisher's research sits in the intersection of earth science, chemistry, and biology, exploring how life and planetary environments have co-evolved over Earth's history and informing the search for biosignatures beyond our planet. So Woody was also a study lead of a recent study at the Keck Institute for Space Studies on the biology of biosignatures. So welcome, Woody. And next we have Abigail Freeman, research scientist at the NASA Jet Propulsion Laboratory, who specializes in remote sensing of planetary surfaces. She's the principal investigator of a next-generation lunar imaging spectrometer and serves as deputy project scientist for the Curiosity Mars rover, with deep experience translating science into mission exploration. Abigail was also a Keck Institute for Space Studies Prize postdoctoral fellow from 2014 through 2016 and co-led the KISS workshop, Revolutionizing Access to the Martian Surface in 2021. So please welcome Abigail. And then from the United Kingdom, we have Timothy Horbury, Professor of Physics at Imperial College London. Professor Horbury is a leading expert in space and plasma physics and is the science lead for the magnetometer on NASA's Interstellar Mapping and Acceleration Probe, IMAP, which was launched recently very successfully, advancing our understanding of the sun, space weather, and heliosphere. Welcome. And finally, Neil Bowles, Professor of Planetary Science at the University of Oxford, who focuses on planetary instrumentation and laboratory measurements that enable the interpretation of spacecraft data, with research spanning asteroids, the Moon, Mars, and the icy worlds of the outer solar system. So please join me in giving warm welcome to our outstanding panelists. Thank you.
It's working. Well, good afternoon, and I want to add to what John and Georgina said about welcoming you to Caltech and JPL. I'm delighted to see so many JPL people here, and particularly I was delighted when I was outside, a number of British scientists came to see me and said, oh, we used to be at JPL from this year to that year, and so on. So that is a reflection of the collaboration, once more reflection of it. Also, I want to thank Harriet and Irene for organizing this. As usual, they always do an absolutely superb job. So thank both of you for that. So I thought, and also I want to mention that Mr. Rainey, it looks like he knows a lot about Caltech and JPL. So I'm delighted to see that you are a friend, a local friend here. Reflecting back, I was asked to say a few things about collaboration, with the UK during my long tenure at JPL. I remember when I was the head of the science division, when I used to go to the third floor where we had all our atmospheric scientists, I used to think that I'm in the UK because almost everybody spoke with an English accent or were trained, in England. Some of you might remember Fred Taylor, Barney Farmer, Dan McLeese, who was also educated in the UK. And then after, when I was a director, I had a lot of interaction with who is presently your royal astronomer, Michelle Doherty, because she led the team who had the magnetometer on Cassini. So I had to meet with her regularly when she used to come to JPL. And when I was a PI, before that, when I was a PI on many flight instruments, shuttle imaging radar, and Cassini radar, I had a number of scientists from Imperial College who were also member of our team. So we go through a long list, and there are many scientific instruments where we had collaboration, with British scientists. And the other person I interacted with, which I have great respect for, is Sir Martin Sweeney, from Imperial College, because in a sense, he kind of started the era of small satellites, developing them for scientific purposes. And I'll come back and talk about that. And I had many, while I was director, I visited many times British institutions, be it university or industry or innovation center. And I was very impressed with the British innovation. I mean, this shouldn't be news for you, but I have to say I was very, very impressed with the innovation that I saw when I visited there. Now, I thought when I was preparing for this, I thought I might want to say something about the future, considering we have American industry, British industry, American researchers, British researchers. So in addition to, I'm sure you are going to be hearing on a number of them, I picked on 3 of them. I think there are opportunities of collaboration on small satellites. UK has extensive experience in that area and in the US, and that's becoming a very popular, activity now. I mean, we're talking about thousands of satellites, be it for telecommunication, for Earth observation, for data centers in space. So I think that's a fertile area where there could be more collaboration on developing advanced, small satellites. The other area is robotics. England had a lot of, or I should say the UK. I have to be careful what term do I use. By the way, my wife and I are going to be in England and Scotland in the summer, so I'm reading the history of how friendly Scotland and England are over history. So I have to be careful what do I use, as appropriate term. So anyway, the other one is Rosalind Franklin experience. That was mainly developed, in the UK, and I could see on future planetary mission as well as lunar mission, we would be relying heavily, on robotics area. So that could be another area of collaboration between the UK and the US. And the other one, which might seem out of the box, is nuclear. Many years ago, we did a major study at JPL on using nuclear power for electric propulsion, to go to Jupiter, and to the outer planet. And we found that the best collaboration was the American Navy, the nuclear Navy, because they had a lot of experience in developing relatively small and very safe nuclear reactors, which have long-term lifetime. Now, that was a period where there was a lot of interest in nuclear at NASA. Then it faded away, but now it's revived again. And England has a lot of experience, in nuclear submarines. So I could envision, both for propulsion as well as for long-term lunar station, that there could be opportunities for collaboration, bringing the experience of our 2 countries, in that area. So I thought these are kind of 3 areas where you might want to be thinking about. I'm sure there are a lot more, and you'll be hearing about a lot more areas, but these are areas where I think deserve, further exploration, of collaboration. So that's kind of, in a nutshell, my introduction. And again, I'm delighted to see so many people from the UK, from JPL, from Caltech, from US industry here. So first, I'm going to start with Woody. I understand, Woody, you did a study for Keck on biology of biosignatures. And there was a number of international participation in it. Can you kind of tell us what was the highlight, what came out from that study?
Yeah, absolutely. So this was biology of biosignatures detection. And what we tried to do was to have some kind of very blue sky bite at an apple that everyone is interested in. And that apple is the kind of, are we alone? Is there life elsewhere? Can we contextualize our own existence here? But to do it in a way that's a little bit different than what missions had been doing previously. Most missions actually are not looking for life. They're looking for evidence of past life or past conditions that could have been habitable for life. We said, well, let's start looking for life again. Of course, we've had missions like this, the Viking mission, for example, and there were sets of experiments. And so it was like, well, how do we I imagine I end up with a gram of regolith from a planet. I declare to you it's alive. How do I demonstrate that it's alive? How are we going to get this? And it turns out this is hugely valuable as an international collaborative problem, because if you take you take 10 Earth or planetary scientists and you say, what is going to convince you that I've found life on a body outside the Earth? The answer is you get 9 answers. So you have to come together and actually start to develop a common rubric that you're going to use to say, okay, I think we can finally develop victory. So we spent a lot of time in our study section trying to understand, well, what would that look like? And it turns out that we all agreed that while there are bits and pieces of evidence that by themselves can have non-unique interpretations, very quickly becomes multiplicative probabilities. And the second that you start to be able to combine a couple different types of evidence for life, you start to have an incredibly robust, meaning we can get everyone in the room, all 50 people, yeah, I'm on board, we did it, we can declare victory. So in some way, if I reflect on it as a kid, the idea of, oh, wow, maybe I'll be the one to discover life on a planet, outside the Earth, that it's going to be me and 1,500 of my best friends from countries all over the world that are working really hard at this effort.
What can you, based on that study or your regular research, can you give some example of potential either instrument or mission that could be done collaboratively, particularly with the UK? I mean, more international, but particularly with the UK.
Absolutely. So this is a great. So we had. You have to understand that when we tried to do this previously with Viking, there were still large corners of the Earth that we thought were sterile. The Atacama Desert we thought wasn't living. And we now recognize that there have been huge breakthroughs in our ability to find life, even when it's not concentrated, even when it's exceptionally rare in rock and mineral samples. So we have all kinds of new technologies. Now, most of that new ability is the ability to sequence DNA out of environmental samples. Okay, but there's a new technology that we talked about a lot in our collaboration that is called nanopore sequencing that allows you to sequence a linear polymer like DNA or a peptide like a protein in a way that's way more agnostic. It allows you to look for something without having to know what you're looking for ahead of time. That said, this technology is in its infancy, and it has a long way to go before we kind of understand how it works better, and then, of course, it could be applied to a future space mission.
Abigail, let me ask you a question. I mean, you have done work on Mars and on lunar and planetary. Can you reflect on the collaboration, particularly with international and the UK? How did that shape, your work?
Yeah, one of my favorite things about space exploration, besides it's being really, really cool, is that it requires so many people to be able to do it. We talk about spacecraft, how it takes hundreds of people to get a spacecraft to explore different kinds of engineers, scientists to define requirements, all these things. It turns out it also takes a huge number of people to operate a spacecraft, and especially something like the Curiosity or the Perseverance rovers, which I work on Curiosity, hugely complex to operate, and also to interpret the data that we collect. Not a single scientist is able to understand everything. You need people with expertise in geochemistry, sedimentology, atmospheric physics. All of these come together to help us really utilize everything we can from these engineering marvels. The Curiosity science team is about 40% international, so almost half of the team is from outside the US, and I think having all of these scientists with totally different perspectives as well as different expertises really enriches the quality of the science that we're able to do. And I, of course, have to give a special shout out to a very important portion of that team from the UK, Imperial College, also Open University. We have team members from. They are a small force but play an outsized impact on the operation of the rover. Always dialing into ROPS. Anytime you dial in an operation for the Curiosity rover, I guarantee there will be at least one person from the UK, probably more than one. late into the UK night, which is only afternoon for us, but really awesome. And then actually did a fun exercise a couple weeks ago looking at the publication record, and a disproportionate number of the scientific publications also have these UK authors. So it's really this amazing collaboration that enriches our ability to understand what we're learning with these rovers and what it tells us about the history of Mars.
Now, I know you are working now on Operation of Curiosity. Has there been any discussion with our British colleague on lessons learned for Operation of Rosalind Franklin?
Absolutely, and this is also, I think, one of the hopeful legacies this rover can leave is that it is training for future rovers. We learned a lot from the first Sojourner mission, which led into Spirit and Opportunity, which directly led into how we operate Curiosity and Perseverance. And I think we're able to take those lessons learned, and especially firsthand lessons learned from UK and European collaborators, to apply to Rosalind Franklin. I know a lot of our team members are also members of the science team for that rover. So I hope they can take how we operate the rover and do it even better for this upcoming, very exciting mission.
Thanks. Neil, let me go to you, hopping across the pond.
Hello.
Now, can you basically say, from your perspective, from perspective of the UK, how did the international collaboration, particularly with the US, affect your research, your interest, and so on?
It's been an absolutely huge enabler of it. I mean, I think the first flight hardware project I worked on was actually for Mars Reconnaissance Orbiter way back in the early 2000s, when we built a very small, but of course I would say important part of one of the instruments on it, the Mars Climate Sounder for doing atmospheric science. And we've really kind of followed that through, and from then Cassini and a whole range of other missions as well. I mean, to the present kind of like era that we're in now, where we're looking at, joint collaborative missions, such as we did the Lunar Trailblazer mission last year, which, it wasn't successful, but it was certainly an extremely important and embedded experience that we had. And I think, and then leading on to other opportunities that we've got. So, for example, there's a very strong, I have an involvement, and you'll probably hear about this later from my colleagues from Rouse Space, but we have a very involvement in the Aerial Space Telescope, which is now, includes a very important American contribution from JPL. So there's a huge amount of connectivity, very deep, wide collaboration that has absolutely enabled the research activities that I want to do. In fact, it's hard to imagine that we would have been able to do a lot of it and build the capabilities that we have jointly without that interaction.
Now, from my experience, collaboration is mostly successful if you started very early at the stage of the definition, of a mission. Can you reflect on how should we be doing early definition of missions to make sure that we have a strong collaboration?
I mean, I think although ultimately we had a problem with the spacecraft on Lunar Trailblazer, that was actually an extremely important process for us, because we were involved in everything from the original proposal that was submitted to NASA all the way through the build and specification and then delivery of our instrument, and then the coordinated operations. Lunar Trailblazer was a small spacecraft. It was one of the NASA Simplex missions, so it was a very small kind of quote-unquote low-cost mission. But so that involved very close collaboration with the people building the spacecraft and very close collaboration with the operations team that were based here at IPAC, actually, at Caltech. And so what we had was this immediate, strong interconnection where we were all working together very closely to meet a very tight deadline to get the spacecraft ready and assembled and tested. So it was absolutely essential. If we hadn't been in at the beginning, and we hadn't had the support also from the UK Space Agency at the beginning of that process through the bilateral program, which is one of the things that we're here because of, we would not have been able to participate, and we wouldn't have actually been able to achieve what we did in the timescale. We went from selection to hardware delivery in 3 years. So it was absolutely essential we were present at the formulation and then all the way through.
Okay, thanks. Now, Tim, let me ask you, you are the science lead on the magnetometer on IMAP. Can you tell us a little bit more about that mission, that instrument, and particularly on your experience in collaboration with NASA and the US?
Yeah, absolutely. And I think I should probably start with a little bit of history as well. Stephanie mentioned Ariel 1, the UK's first satellite, which was a collaboration with the US. So Imperial College had an instrument on that mission. And actually, we at Imperial end up in a position where we do have a space hardware capability because of that sustained long-term investment by the UK government into our instrument capabilities. And I think that's a really central aspect of enabling all of these collaborations, is having that long-term sustained investment. So Imperial College has chosen to specialize in space hardware, mostly in magnetometers. And so we've ended up in really a world-class position, and that lets us get involved in lots of different missions. You mentioned Cassini. And of course, so we led the magnetometer from Cassini. And in fact, I first visited JPL in 1994 as a PhD student because I was working with my PhD supervisor, who was the lead of the magnetometer on the Ulysses mission. Ulysses, European mission, but with a magnetometer which was joint between JPL and Imperial College. And so we have very long, deep collaborations on these things. So for IMAP, we were actually approached by the project team after selection, actually rather later on in the process, precisely because we had a very successful magnetometer design that we were flying on Solar Orbiter. And they needed a magnetometer relatively quickly. And so we worked very closely with the UK Space Agency through the new international line. And actually that funding opportunity was really the way that made it possible for us to collaborate on that mission, which otherwise is very difficult. And so those new funding sources to let us collaborate with the US have become incredibly valuable to us to get involved in those missions. So IMAP has been a great success. We ran very fast to get it done. So Helen and the engineering team got the instrument delivered within 3 years. IMAP has launched, is working really successfully. And actually, one thing I would say about it as well is it's a scientific mission. So its science is about how the heliosphere interacts with the local interstellar medium and also energetic particle acceleration. But by going to the first Lagrange point upstream of the Earth, it's also a space weather mission. And so our instrument is a scientific instrument, makes scientific measurements, but at the same time, it's a really vital space weather monitor. And so I think this is a really nice example of how you can fund a science mission that also lets you do something that has societal impact. So as you might have heard, there was a very big storm yesterday. There were very big auroras, even across America. We measured that with the IMAP magnetometer. We were seeing that in real time. We knew it was going to happen. And actually, Solar Orbiter at the moment is actually even further upstream of the Earth. Solar Orbiter goes closer to the Sun than Mercury. It has a very complicated orbit. At this moment in time, it's almost directly upstream of the Earth, about a fifth of the way to the Sun. And in fact, our magnetometer on Solar Orbiter in real time measured that event about 6 hours before it arrived at the Earth. So we could tell you it was going to be a big event. So these things, again, they're science instruments. They let us do space weather as well. And actually, Artemis 2 is coming up. If Artemis 2 stays on schedule, Solar Orbiter will also be upstream. And so we will be in a unique position with these two spacecraft providing real-time space weather monitoring for the first time that humans leave the Earth's magnetosphere in over 50 years.
Now, Tim, I'm very familiar with the magnetometer activity at Imperial College, and you guys are first rate. Can you speak a little bit broadly on interest in the UK in heliophysics? I mean, not only at Imperial College, but across the country?
Yeah, it's a really growing area. And in fact, in Europe, it's growing hugely as an area of interest. And that's partly because in heliophysics, we're in a new golden era, and that's partly because of Solar Orbiter, which is bringing together solar remote telescope measurements as well as in situ measurements, and that's combined with Parker Solar Probe, which of course is a NASA mission, which is going extraordinarily close to the Sun, flying through the Sun's atmosphere. And this really is giving us a renaissance in the field, and that combined with other missions, the European Bepi-Colombo mission that's going to Mercury is also taking measurements, the Stereo spacecraft, NASA mission, and Earth assets as well. We're in a unique position now we're essentially taking measurements globally around a star in a way that we've never been able to do before. And so we find ourselves, through international collaboration, in a really unprecedented position. And some of that is fortuitous. Nobody planned these missions to fly at the same time. They have come out that way, sometimes because things were on schedule, sometimes because other things weren't. But we've ended up in a really extraordinary position. And as a result, the field in Europe is growing enormously. It's hundreds and hundreds of people now. It's a huge success story, I think.
So let me now ask all the panelists here. I mean, here in the US, we have what we call the decadal plan, which has worked with the academy to lay out what are the strategy for the next decade. I assume there is something similar in England, that collaborate. How do you see the two from both? I'm going to ask everybody.
Yeah.
How do you see those two things? Are they aligned? Are they natural for collaboration? And it doesn't have to be only space, but also in technology and scientific research. Go ahead.
Okay, so in the UK, there's just been a recent process for collecting white papers in a fairly similar but faster mode than it's called the Space Frontiers process, and it's being led by Adam Amara, the chief scientist at UKSA, who you heard from earlier. And that's sort of like collecting together where the community wants to be and what it sees its priorities in a fairly similar way to the decadal process does in the US. Of course, we are going to be broadly aligned because we have broadly similar research interests, and also because the big questions that we want to answer are universal. And so, they all line up with, why is the moon made what it is? Why, is there life in the universe? What is dark matter, et cetera, et cetera. So we have a broadly well-aligned set of scientific goals, and we're going through a process in the UK of sorting those and seeing them. There's also, of course, ESA processes as well. They have a thing called Voyage 2050, which leads to missions such as one of the deeper future missions is a mission perhaps to Enceladus, to do measurements there as part of that process, which lines up again with the kind of ocean worlds, icy world stuff, that moons that studies on the US side.
Yeah, absolutely. I think the New Frontiers process will be really fascinating to see how...
You're pointing there, is that for the chief scientist?
Oh, I'm sorry. Adam
okay,
is the one who's leading that process.
Who they are pointing to.
Sorry. So I think that process will be really fascinating to see that comes out, how the UK as a community can make some prioritizations there. I think also... obviously, the UK is a smaller nation than the US, and in some ways can't influence things in quite the same way. But still, I think nevertheless, in the way we choose missions to be part of and collaborate with, helps us influence that process as well. And so, I mean, from a personal perspective, we're also building the magnetometers for the upcoming Helioswarm mission, which is a 9-spacecraft constellation. So again, the UK is funding us to do that. And that's a mission which is really about solar wind turbulence, but will fly through the magnetosphere. And so that will help to address some of the science goals that have come out as the priority out of the latest heliophysics decadal, which is about global magnetospheric monitoring. So I think we can also find ways to collaborate to take advantage of the missions that are available to do the science that we want to do.
Abigail?
Yeah, I mean, I think an area, at least that I'm most involved in, that is obvious collaboration between the two countries is in Mars and Moon exploration, just deep experience in both. And, I'll put in a plug, not quite decadal level, but 2 weeks ago I was at the Lunar Exploration Analysis Group meeting, and the community expressed, a lot of enthusiasm for continuing to get data about the moon, and in particular the data that the Lunar Trailblazer mission was going to collect about water and ice on the moon, and optimistic about a future where we can still get that data. NASA has selected the instrument that I'm the PI of, the ultra-compact imaging spectrometer of the moon, to fly again and recover some of the data, or all of the data, that the imaging spectrometer that was built at JPL was going to collect at the moon, and then looking very optimistically to our UK friends to see if we can get Neil's instrument, because the two of them working together, their sum is greater than their parts. And, it's this kind of exploration of fast, cheap commercial missions maybe, but can we, if we don't get the science that we were hoping to get, can we try again? And optimistic for that future in this really strategically important data set.
I have not much to add, but I'll mention something that hasn't been brought up is that it is so valuable to have a healthy international conference that is just, you've got it every year, and it has good attendance, and people see value in it, to maintain these types of relationships that have to simmer for a little bit before they start to become a strategic plan.
I think you touched on my next question. I'm going to appoint the four of you on a panel, including Adam, so be prepared to answer, for a panel to define the next 10 years of joint work between the UK and the US, be it in science or technology. What would be your most important advice that you would give, or you suggest? Now, you suggested a bunch of meetings at Keck Institute, so you're advertising that for Harriet. But do you have any other advice or suggestion of how to proceed, how such a panel should proceed, and what would be the priority?
This is maybe highly, for those that know me will understand why I say this, but it is so valuable that I have a relationship with, it's just a handful of PIs that I really like working with. I believe in them, their lab, their students. I hire them, I hire their lab, I hire them, and that's just part of a pattern. And that becomes, and then that just that grows missions.
Okay.
This is a big question. I think there's a lot that we can do. I think the 3 areas you outlined at the beginning were excellent. I'll settle into the robotics land, and I think in terms of robotics and continued robotic exploration of our solar system, especially the Moon and Mars, I think really aligns well with the priorities of both countries. And so I'd love to see continued missions, more missions to the surfaces of both planets. There's so much more to discover.
Yeah, amen to that. I would say something slightly more maybe technical that some of us were talking about earlier on when we were up at JPL. I have a really strong sense now that launch costs have come down so much. The capabilities of platforms have increased dramatically, and actually the cost of platforms has come down a lot. The scientific instrument costs haven't really come down in the same way. And I think as a community we need to work, and actually I think the agencies can support us in finding ways to get more done for the same amount of money. And I think there are ways we can make those instruments more quickly, just as capable at lower cost. We're seeing that with Helioswarm. We're producing 9 instruments for less than twice the cost of 1. These things can be done, and it's hard, but I think collectively we can think about how to make more output with the funds that we have available to us. And I think that's something we can all collectively work at and try to be better at.
Yeah, and I think I'd echo that in terms of the technology. We're in a weird sort of inflection point now where the traditionally very expensive parts of the mission, particularly for the sort of Earth environment, near Earth environment, and also the Moon, the costs have come down for the launch dramatically, and the actual spacecraft are becoming more or less commodities now that you launch on. So then that means that the kind of traditional cost balance is switching back towards the instruments, which is kind of an interesting thing. And also we have much more opportunity for exploring in this part of space. I think, though, for sort of a general 10-year sort of technology, I think it's just being able to maintain the collaborations that we have, and they really help build into the future. We have wide, expansive networks of former students and postdocs. We exchange postdocs from between the United States and the UK on a very regular basis. We've just got a new one starting in my colleague Carly Howart's group at the beginning of last week, for example, and they're going to be studying the icy moons and working on Europa Clipper, and things like that. So that's a UK position, but filled by an American at the moment. And they will hopefully gain a lot of experience working with us and then go back to the United States and remember this. And we have similar exchanges of information. There are lots of people in this room who have spent time in the UK or spent time in the US. So I think being able to maintain that connectivity, being able to maintain those networks, I think is a really good thing. And that's something I'd really like to see strengthened and maintained. I think apart from that, we have a very exciting 10-year program. A friend of mine says, if you ever have to use the word exciting, you should never use the word exciting in a proposal because it means it isn't, which, I think is probably good advice. But certainly I do think there is a lot of exciting capability coming along. So, for example, the aerial mission has a strong US involvement in the detectors, which are used in the near-infrared part of the instrument. That's going to be probing and surveying the planet, the atmosphere is around 1,000 or so exoplanet atmospheres. That's going to be really interesting. It feeds into some of these grand questions we have about, potential biosignatures, maybe, I don't know. I'll just go with that for now. You've got the kind of wider exploration, the whole human exploration side of it, where we will have probably people on the moon towards the end of the decade. And, they are incredibly capable people. You've just seen the amazing sort of story from Megan earlier. Imagine having somebody like that on the moon picking you up a rock, We haven't had anybody doing that for 50 or 60 years now, and that's going to be transformative along with the technologies that develops. So I think the sort of general momentum we have in exploration and the science elements are really brilliant, and I think that's where the excitement is going to come genuinely, I think, in combining those capabilities. So I think there's a lot of capability in the room. There's lots of people here. For example, UK has fantastic deep space network capabilities, which through people like Matt Cosby and the Goon Hilly Earth Station, they really helped us out during the Lunar Trailblazer moment of excitement after it launched, and I'm very grateful to them and also UK Space Agency for their support. But that sort of non-traditional groupings and abilities to bring in industry into those areas and how this sort of technologies are also where we're at. So we've got this really interesting exploration, science convergence, industry coming in, providing solutions in different ways, sometimes where traditionally it was a main government customer, things like that. And this is a really exciting time to be doing this kind of work.
Okay, thank you. While you are giving the microphone to Adam, Georgina, I'm going to put you also on the spot, asking the same question. So how would you recommend that should we proceed to develop a joint program, if you want, of joint activity between the UK and the US?
Right, yeah, so from the UK perspective, if we take a step back, we've got a very long established working relationship with ESA, and it's a fantastic way to deliver a large part of the science that we want to access. But the ESA work engine is remarkable at the sort of ML class range, so 500 million to 1 billion, that's the sweet spot. We do really, really well. And working with the US, we can continue to do work in that area, but what I'm really excited about is broadening the diversity, being able to access things that are way beyond that. And we know from our experience with Webb that we can go much, much bigger in partnership with the US, and that's where I see Habitable Worlds Observatory as a great galvanizing sort of experiment that kind of transcends any sort of national border you might think about, and we want to be a part of that. But also at the very small end. So I'll go back to what you said, Charles. I meet with Martin Sweeting quite regularly, and it's really quite inspiring to have that radical way of looking at how to put experiments up into space. So I came to JPL for the first time in 2005 when we had early discussions about the precursor that became Euclid, right? And here we are in 2026, and don't get me wrong, I'm very excited that this year we'll get our first cosmology results, but that's a very long time to wait between, hey, wouldn't it be great to do this, to having the data. And so being able to create a pathway for especially young, new, bright-eyed UK academics who have an idea and they want to turn it around really fast and get that training they need to be the PIs of the future at bigger and bigger scales. So I think there might only be one Habitable Worlds Observatory, but at the small end, using this new space approach, I'm hoping we can develop a pipeline. And for the UK, there's been sort of a debate a few years ago about a UK only mission. I think the way I've landed is I'd much rather that we have a bilateral program that allows flexibility, where at one end of the spectrum, UK does lead the mission and invites a place like JPL to be the minor partner, and I think that would be great. And then we've created similar programs in ESA, so we've created a little ecosystem at this small end. So that's the bit where I think it's a unique opportunity to work with you that would create something truly beneficial for the ecosystem.
Thank you, Adam. Do you mind to bring the microphone to Georgie? No, I know.
Yeah.
Oh, you have one. I know you are not. You cannot speak for NASA, but I think JPL has some influence.
Yeah, absolutely. And honestly, I would echo what most have said on the panel. I think we are at a real inflection point, actually, when we look at this new administration. Some of the expectations that are coming out are certainly of Administrator Isaacman in terms of what he is looking for in service of the new administration. It is to accelerate science, right? It is to make sure that we can do more faster, invite more risk into the mix. And I think that's something we very much are looking at in terms of at JPL is how do we diversify our portfolio? How do we support NASA more broadly in terms of what they are looking for, whether that's more human exploration, whether that is more faster turn science missions, whether that is, certainly being that conduit to industry to, again, bring costs down and move a lot faster. So I think that is a real rich area for us. And I think Adam said it so eloquently just then, is like, how can we work together on that? And Administrator Isaacman issued a memo today to employees, which was very much around the acceleration of science and not having to wait decades for those findings. And I think you're going to see a lot, now we have some stability, hopefully, around budget, a lot more fast decision-making around, okay, what do the next few years look like in terms of smaller missions where we can get quicker science results back? So I see it as a different a pivot, certainly in terms of how NASA and certainly how JPL, how our portfolio has been made up over the last number of decades, but a really interesting, exciting time. I don't want the word exciting now is imbued with, okay, it's not exciting, but genuinely exciting time to really do more of things like this and do that cross-sharing. So,
well, we have a few minutes for a question, but before that, many people mentioned JPL, Caltech. I'm curious from our British guests, how many of you have worked or spent time at JPL or Caltech? Can I see a show of hands? Oh, fair number. Okay, I'm delighted to see that. So now, I mean, we have, before Harriet throws us off the platform here, but if you have any question, please say your name, organization, so we know where you are from and who are you addressing the question to. Any questions? Oh, please.
Yeah, thanks so much. Just really a question about, you talked a bit there about the private sector dynamic, the kind of falling cost of launch vehicles, the kind of fact that sciences remain pretty static. Do you foresee things in that kind of private space journey where they're going to hit a wall at some point, or there are unforeseen elements that, obviously having been in science of space for much longer, you've kind of been like, now we know this is coming, or these are the things that could really derail you? Because at times it seems like it's a perpetual, it'll all just work, it'll all be fine, and we'll keep making rockets and keep moving fast. But I'm conscious in the kind of 90 plus years of the kind of space exploration journey, there's probably things that you've seen that they haven't. And I'm just curious to see if you think where that might be a moment of reflection. I don't know who's best placed to reflect on that. Was kind of my curiosity about the private versus the public space.
Okay, who would like to answer? Go ahead.
Oh, okay, right. Yeah, no, it's a very good point. And these things kind of go up and down. We've heard about faster, better, cheaper, which wasn't entirely successful. So there's a real balance here. And I think you need some kind of risk portfolio. You need to understand how fast you can push and what risks you can take and what risk you're willing to take, so what your risk appetite is like. And I think you need a blend, as Georgina was saying. I think you need a balance of those things. I think new space can learn things from people who've been doing it for a long time, but equally I think we can learn things from new space. And the way, like what do we need to do? What part of this process is necessary? Where are we taking risk? Where are we not? And I think we can all get stuck in processes which maybe aren't necessary so much. It's quite hard to change, I think, and it's something that I think we all grapple with. As I say, for us, we've been forced to do it because there's a mission where we have to build 9. If it takes 3 years to build 1, that's not going to work. And so we've actually had the opportunity to sit down and think about how we can do it differently, because if we don't do it differently, it's not going to work. So I think it's this idea about how do we sit down and collectively decide an approach which will work, which will work, which won't introduce extra risk, but we can do it faster. And I think we can learn a lot from some of those new industries. And actually, of course, this area is full of that capability. I mean, there's nowhere like it on the planet. And so I think the companies we were visiting yesterday, VAST and Rocket Lab, whatever, I think there's enormous amounts to learn from those kind of companies.
So there was a very interesting discussion with colleagues at JPL this morning around this sort of area. And I think one thing you have to be quite clear on is, I think, the sort of quote unquote new space approach, which is really just code for not old space, which I don't really, it sounds a bit weird, but you know what I mean. Essentially, I think it can be used for low Earth orbit and the moon, where you've got plenty of opportunities to launch. And you can get, you can go to the moon kind of once a month-ish, unless you need to land in a specific season or something. But when you're talking about further out in the solar system, it becomes a little bit more complicated. So if you're going to Mars, one of the comments that was made this morning was you get a launch opportunity every 26 months or whatever it is. And so you can't do the fail fast approach for that, because your program all of a sudden becomes fail slowly. And you're throwing things out there which may not work, and then it takes you time to relearn them. And I think that's actually a really important thing to think about, is celestial mechanics, unfortunately, will get in the way unless we get a fantastic new propulsion system or something, which will allow you to do direct transfers. So I think that's part of the thing. There will be a very distinct role for the high reliability, longer term planned projects, the sort of big flagship type missions, to places beyond towards Mars and then into the outer solar system, they will still continue in the same way, and they will almost certainly remain strongly government involved. But for certainly the sort of cislunar environment, I think there could be a really big change coming, where the CLIPS model is a good example of this. We have commercial providers for landing on the moon, and then you buy a slot on it on the spacecraft like a service. And that sort of space as a service approach is going to become more and more and more important for those exploration goals. But there will still be a need for the very carefully planned high reliability, where you just don't have the planets don't line up for you in the way you would like. Yeah.
Anybody else? No?
Sure, yeah, well, I'll just say balance is a great word. I was gonna say sweet spot between a mix of what commercial and what government academia can do. I would phrase it in terms of the types of science questions that are answerable with the technologies that are offered by these different organizations. And I think the more we explore, the more complex our science questions become, and the instrumentation and the spacecraft required to answer those questions, be it at Earth, Moon, and beyond, there are some things that just are not achievable or profitable by what industry is offering.
Well, I think we are almost done, but as a moderator, I have the last word to answer a little bit, kind of your question. There is this lab up the hill called Jet Propulsion Lab, but there is no work on jet propulsion in it. We used to do jet propulsion many, many years ago. So all the propulsion rocket and so on, we buy them from industry. So there is already, and most of the spacecraft, when we say spacecraft is being done in-house, that means almost half of it is being done in industry, and we integrate it. So already there is a lot of work between the two places. But the key message, particularly for people from the UK government, the government has a critical role, because industry tend to think about the near term, the next 4 or 5 years. And they think about what makes them more money, which is what they are supposed to be doing. That's why I buy stocks in them. But you need somebody to be thinking about the long term, where you have very high risk, where you really are willing to invest in pushing the frontier. Industry, most of it, will not do that. I mean, I remember an episode after I left JPL, I was on a board of a company, I'm not going to mention who it is. And in my first meeting, one of the employees comes in and briefs the board, and they talk about this new development they want to do. And the first question the CEO had, how much money will that make us? And I kind of laughed, and I told him, so, I never asked in my 40 years at JPL, I never asked that question. I always ask, well, how much is that going to advance? And then once we develop the technology, then we turn it over to the private sector or work jointly with the private sector to make that happen. And rockets is only one example. Telecommunication is another example. Coding, all the things which are done by the Deep Space Network were really started between Caltech and JPL, and now industry is doing that. So there is still a very critical role, particularly talking for the leaders from the UK, there is a critical role for industry, for the government in investing in those areas. Again, thank you all very much, and I hope you enjoy the rest of your stay here.
So we are going to move on to our lightning rounds in just a minute. While we're getting settled here, just a reminder for those lightning talk speakers, we've got a list here. You can see that we have got a great number of folks that we're going to hear from in the next hour. So if you see your name on that list, please do come up here and get ready so that we can keep flowing through speakers by speaker. We're going to have 3 to 5 minutes max from each of our speakers. You'll get a 3-minute warning. You'll get a 4-minute warning. When you see me gently walking up to the stage, that means that we are moving on to the next talk. I'm going to control the slides, so we are going to keep to time. I just want to say a huge thank you again to our fantastic panel that we just had. That was a fantastic discussion. Let's do another round of applause for our panelists. And with that, we're going to segue into our lightning talks as well. So first up, we have Jonathan Lunine. Jonathan, over to you. Thank you.
Okay, so 21 years ago this month, the Huygens probe landed on the surface of Saturn's moon Titan, 1 billion miles from the Earth. That's 1,000 million miles from the Earth. And this was an amazing mission, a remarkable success for the European Space Agency. And it was a remarkable collaboration as well, transatlantic collaboration. And we are going to get the slides in a few minutes. Is that right? Harriet, do I do the slides? You do the slides. There we go. Okay. So European Space Agency, NASA, and Italian Space Agency, and all the instruments produced by various instrument makers in nation states in Europe and also in the United States. And so next slide, please. So the Huygens probe was carried to Saturn and Titan by the Cassini-Saturn orbiter, which was built primarily here at the Jet Propulsion Laboratory. You see the Huygens probe as the gold-covered disk in the center there. There were a number of UK scientists on the Cassini and Huygens mission. I'm just showing you a few of them. David Southwood, the PI of the magnetometer, who became the head of space science at the European Space Agency. Michelle Doherty, who was then the PI for the magnetometer and is now the 16th Astronomer Royal of the United Kingdom and the first woman to occupy that role. And John Zarnicki, who was the principal investigator of the space science package on the Huygens probe itself. The other two were on the Cassini-Saturn orbiter. John just retired from the Open University. And I want to highlight in my little time that I have the fourth of these scientists, Ralph Lorenz, a UK scientist who began as an engineer on the Huygens mission, realized that science was more fun, got his PhD under John Zarnicki at Kent, and if we go to the next slide, played a key role in determining for us that there really is liquid at the Huygens landing site. So in the upper left-hand picture, you see an image as the Huygens probe descended by parachute through the dense atmosphere of Titan, a mostly nitrogen atmosphere 4 times denser than the air in this room. Very, very cold. Remember, 1 billion miles from the Earth. So water is completely frozen out at minus 180 degrees Celsius, colder than Antarctica. And so those gullies that you see in that picture could not have been formed by running liquid water. They had to have been formed by the condensable gas in Titan's atmosphere, methane or methane, depending on which side of the Atlantic you are on. And when the Huygens probe landed, it saw these boulders in the center there, rounded and tumbled ice and organics. But the surprise was that after landing, the mass spectrometer recorded methane coming out of the ground. And so that upper right-hand graph from the mass spectrometer built at Goddard, and I was a co-investigator on that, showing mole fraction versus time during the mission. That's the methane signature. The red vertical dashed line is the landing time, and after landing, whoof, methane starts coming out of the ground. But was that methane a gas or a liquid? Well, there was no way to know from the mass spectrometer. But Ralph, who had built sensors on the surface science package on the Huygens probe, had a very clever idea, which was to use the heater on the inlet of the Huygens probe, which was at the bottom of the probe, and therefore it was immersed in the ground upon landing, to look at the temperature profile and from that decide whether there was a latent heat of evaporation or vaporization that might be coming from the methane that would buffer the temperature and tell us that that methane indeed was a liquid. And sure enough, in a paper that he led in 2006, it was demonstrated quite convincingly that this really is liquid methane. And so the Huygens probe sampled not only the atmosphere, but the working fluid of Titan's meteorology right at the surface at the landing site, methane. Ralph would go on to APL. He worked with me actually for 10 years when I was at the University of Arizona, wonderful collaboration. Went to APL, he's the mission architect now for the Dragonfly mission, which will be launched soon to Titan, and we'll do more exciting sampling. But in this year, after that analysis was done, the radar system on the Cassini-Saturn orbiter, which was led by Charles Alachi, discovered vast lakes and seas of liquid methane on this object, which in some ways is the most Earth-like in its geological processes, but the most exotic in terms of the materials that those processes work on. Thank you.
All right, fantastic. And thank you for Jonathan for setting a fantastic example on timekeeping. Next up, we have Hao Cao. Over to you. Thank you.
Next slide. All right, good afternoon, everyone. So Jonathan mentioned, 21 years ago, Huygens landed on Titan. 12 years ago, I got the privilege of finishing my PhD working on data from the Cassini magnetometer, led from Imperial College London. Next slide, please. Now, I want to give you a highlight of some of the science that Cassini magnetometer has enabled us to do, but I also want to mention that right from the beginning, the Cassini magnetometer instrument is a UK-US collaboration. As it proposed and as it flown, the Cassini magnetometer consists of two sensors, one vector scalar helium magnetometer built at JPL, and a flux gate magnetometer sensor built at Imperial College. So you will see this a boom on the left of the Cassini spacecraft. That's a 11-meter long boom. The vector helium magnetometer is at the end of the boom, and the flux gate magnetometer is at the middle of the boom. Many of you may know the story that after about a year, the arrival of the Cassini spacecraft at the Saturn system, the vector helium magnetometer stopped working. So most of the science were achieved with the Imperial College flux gate magnetometer. But this whole endeavor was a UK-US collaboration right from the beginning. I'm from UCLA, I also did my PhD on this from UCLA. Now, how did the UCLA scientists become part of the team? That's also a very interesting story. Now, UCLA independently bid for the flux gate magnetometer, as we do have a lab built magnetometers. We didn't want, right? We lost the bid. Now, as the NASA rule that the team that won the bid are asked to invite all competitors to join the team, which they did, and that's how the UCLA scientists became the co-eyes of the magnetometer instrument on board Cassini. I do want use the rest of the time to highlight a few of the science discoveries. One of the highlights of the Cassini mission is the discovery of the active plume from Enceladus. And the first evidence of that was spotted in the Cassini magnetometer data rather than in imaging or other instrumentation. The magnetic field measurements also allowed us to say something about the interiors of Saturn and its mysterious dynamo, as well as Alfvén waves being discovered inside or planetward of the D ring at Saturn. Jonathan mentioned Titan. Titan doesn't have its own magnetic field, but it forms an induced magnetosphere, and that changes depending on whether Titan is inside the magnetosphere of Saturn or exposed in the solar wind. And last but not least, Cassini magnetometer measurements allowed us to understand the magnetosphere of Saturn, inside out. Next slide. So I do want to show a picture of the Cassini mag team right after the Cassini mission ended. And so that was actually taken here at Caltech, right next to South Mud. Harriet, you might recognize the background of the picture, showing the members of the team, and including David Southwood, the original PI of Cassini mag, Michelle, and also I included a few photos of key person on the Cassini mag team not included in that photo. And if you do a count, you will notice about 40% of the scientists here are US, about 60% of them from the UK. So thank you.
Fantastic. All right, next up we have Shalay Nexad. Over to you.
Thank you, Harriet. I met some of you as laboratory's chief technologist, but I have the pleasure of telling you about the work that's my own and my team's about ultraviolet detector technology in the context of our collaboration with the UK entities. Now, ultraviolet is a very challenging part of the spectrum for detection, that all those great images that you carry with yourselves are blind in ultraviolet. And we have been working, and you can go advance the slide, we've been working on, for the past decade or two, making really high efficiency, stable, uniform, radiation tolerant UV detectors out of silicon. And our work starts when industry leaves off. The work that we've been doing, it's technologies that we've been developing are compatible with the foundries. We also influence and do the design of the detector sometimes, but the technologies start after the foundry ends. And we do it in a way that is compatible with large wafers and it is agnostic with any kind of detector design. It could be CMOS, CCD, EMCCD, anything. And it's commensurate with the space missions, cost and schedule in a way that is high throughput and high yield. And so we've been working with various industries, and the work with Teledyne E2V began with a challenge that was given to us about 10 years ago by the PI of Galaxy, who had an idea for a follow-on Explorer mission. And the idea was, can you make detectors that are photon counting and have a factor of 2 better efficiency than Galaxy detectors that are microchannel plates? And so we started working with Teledyne E2V, and I won't get into the detail of the challenges of starting that, but it's been great since then. And we achieved a factor of 5 to 10 better efficiency than those Galaxy detectors. We achieved, and that was so exciting, and it was such a successful collaboration that we continued. We delivered detectors to Fireball, which is a balloon and has had 2 flights. You see, we even overachieved and had an 80% quantum efficiency for the Fireball. And then we expanded our collaboration to extend these developments that we've done beyond electron multiplying CCDs or EMCCDs. So I'm very excited to report that we had the successful launch of Star Planet Activity Research CubeSat, or SPARCS, last Sunday at 5:40 a.m. It had the launch. And that is for the first time we have silicon detectors that are really high efficiency in UV and are cutting out the unwanted visible light. So that's now in space, and we are getting good results out of that. And so again, this was encouraging. More results came out of this, and more ideas came for science and for missions, explorers, pioneers, many classes of missions. So we started an end-to-end qualification of our processes with Teledyne E2V, and started also working with Open University. Jasper will tell you a lot more about the results of those collaborations. But suffice it to say that working with OU has been wonderful in the sense that we can now get more rapid development, and our results are also validated. We can get more absolute quantum efficiency measurements. So we can go to the next slide. So we have extended, again, the work into CMOS. CMOS has grown a lot in the sense of as a scientific imager. It's now we are working toward deep sub-electron noise, and we are applying these same techniques so that we could get really high signal-to-noise ratio scientific imaging and detectors in space. And this work is toward hab worlds, HWO, as well as CASTOR. Again, you will hear in the next talk a little bit more about that, but CASTOR is a Canadian Space Agency concept that needs a large aperture UV space telescope. So in addition to working on technologies together, we've been exchanging personnel. Nathan Bush, who started his work in Roman Space Telescope's coronagraph imager, he started that work in Open University, then he moved to JPL and continued that work, and he's now working on CMOS. And and Gillian Kine, I had hired at JPL, she's now at Open University. I do want to give a shout out to the work that was funded by STFC with Rutherford Appleton Laboratory that was developing soft X-rays, and that was a very successful endeavor as well. So we hope to continue this kind of work together.
Perfect. Thank you so much, Shalay. All right. Next up, we have Jesper Scottfeld from the Open University. Over to you. Thank you.
Yeah, so I'm Jesper Scottfeldt, Senior Research Fellow at the Open University. I'm going to continue a little bit what Shule just talked about. The Center for Electronic Imaging is a collaboration. We work very closely with Teledyne e2v. So if you go to the next slide, please. We started when Roman needed a photon counting detector. JPL identified the CCD201 as electron multiplying CCD, which means that the signal is multiplied before it's read out. And that could therefore be used as a photon counter detector. But in order to survive in the space environment, some space qualification had to be done, which we did at the Open University. So we did extensive characterization, radiation damage testing, which basically means taking the device to a proton beam and firing protons at it, and seeing how that affects the output. And so first of all, we identified some ways you could optimize the operation of the device, but also some changes that could be done to the pixels and the readout circuitry itself, and to improve the performance of this after space and it's been irradiated in space. So all of this work was done closely with JPL. Like Shule said, Nathan Bush did a lot of that work, and several test devices was developed and tested, and this CCD311, which is now the flight model for Roman CGI, is now been fully tested and is ready to fly when Roman is launched. So you see there's some example of we identified what kind of damage is done and how to mitigate that best. Next slide, please. So after that, we have recently been working with JPL on. There's some images missing. Oh, we've been working with JPL on this delta doping technologies and coatings. Oh, there they come. So we've been taking the detectors that the Teledyne e2v detectors, which has been applied the delta doping technology and the coating technology to the UV calibrated facilities to test how well they perform. And you can see here that you get so this detector was especially for the Castor mission, which has a UV band from 150 nanometers. So JPL had designed a coating that was optimized in that band from 150 to 300 nanometers. As you can see, you get really good QE performance in that band. And then you can see how you can, by changing the coatings, you can sort of optimize the performance in different wavelength bands. So, of course, this work leads on to the next generation of detectors from Teledyne, how to improve those and to get them ready for future space missions, especially Castor and HWO, and the many different instruments that will have different requirements on the detector, the performance, and in both in wavelengths, but also in how to operate the detectors and the noise level. So we are working. Hopefully, we'll be working with JPL in the future as well on getting these detectors to operate in the most optimal fashion. So that's it for me. Thank you.
Fantastic. Thank you very much, Jesper. All right, I'm going to move out the way because next up we have Carly Howard from the University of Oxford. Thank you.
All right, good afternoon. Afternoon, everyone. Yeah, if I haven't met you, my name is Dr. Carly Howitt. I'm a professor of space instrumentation at the University of Oxford. And we wanted to take this opportunity to talk to you all about some of the work that we've been doing there. So you've already heard from Neil Bowles, my colleague, but also with great thanks to the teams that we've been working with. I think this is a great picture to get the show off the road. I don't know if you can see the details, but this is a picture of the InSight lander, and you can see the Oxford logo that's in the middle. I don't know if we have, is this a laser pointer? Yes, okay, the Oxford logo. But also next to it, we have Imperial College London and JPL. And this was obviously taken on the surface of Mars. So we have a long history of working with our friends and collaborators that are in this room today. And this extends, oh, can we go to the next slide? Do I press the button? You press the button. Okay. And so some of these are some of the examples. So the Oxford team have a long history of developing thermal instruments. These are the most recent, but for anyone that was on Cassini, we were involved in helping to develop SEERS, and that's the instrument I worked on for a long time and know a lot of you in that capability and capacity. But we were involved in the Diviner, which of course was on Lunar Reconnaissance Orbiter. We're on the MIRI instrument, which is on the ESA Comet Interceptor mission that will be launched soon to go and intercept a comet. And of course, the Lunar Thermal Mapper, which was on Lunar Trailblazer. But also, some of you might not know that we're involved in other missions, particularly seismometers. So we have developed sensors for both InSight and for the Far-Side Seismic Suite. And we're involved in the filter assembly on the LaForge instrument on the Canadian LEAP rover. And we're developing the ground systems, helping to develop some of the ground analysis for aerial. And so these are done with lots of the colleagues here, both at JPL, at Caltech, and at other institutions. And so we've got this long history of working together, and we're trying to move this forward as we continue to explore the solar system. And so I have a history of working in the outer solar system. And so one of the things that we've been working on is taking this heritage instrumentation and moving it to the possibilities of working into the outer solar system. So if we could go to the last slide, please. So one of the things we've been doing is taking this baseline instrument, the thermal mapper, and making it ready for Enceladus. And so we've already done, this has been in conjunction with the UK Space Agency, and we're very grateful to their bilateral program. They funded us to do some radiation testing, so we were able to look and see whether this instrument that's primarily been operated in the inner solar system would work as well in the outer solar system, and we're pleased to say it did. And so this is already baselined on the ESA L4 mission to Enceladus, and we've been working with some of the teams at JPL and Caltech as to getting this onto the NASA New Frontiers AO. Obviously, the AO is pending. We don't know what that's going to look like, but we're really excited to continue this line as we move forward and to explore the outer solar system. I'd be a little bit remiss in the last minute or so of what I have if I didn't mention any of the modelling that Oxford's well known for. So, of course, some of you in the room have used and have based your life around the Nemesis, the model, which is a radiative transfer model. I left atmospheres behind quite a long time ago. I'm more interested in surface science. And one of the new models that we've been developing is a new thermal model that's very highly capable. And we used some aspects of it to look at Enceladus recently, going back to our SEERS data and our time on Cassini to show what the conductive heat flow of Enceladus is. And this was a really difficult measurement to make, but it showed for the first time that Enceladus's heat flow is in balance with the amount it probably gets. So that means the ocean isn't thinning, it's not freezing. Very good for life. And so we look forward to making similar measurements as we move into, we start getting e-themis measurements and other good stuff. Some of the work we're doing right now includes making predictions. What might activity on Europa look like when e-themis gets there, when JUICE gets there? What sort of measurements would we need in order to be diagnostic of plumes or in other types of activity? So we've enjoyed working with you all in the past. We look forward to working with you again in the future. And if you're interested in any of these things, please do come and find myself or Neil, and we'd love to continue those dialogues moving forward. Thank you.
Fantastic. Thank you very much, Carly. All right, next up we have Martin Barstow. Thank you.
Okay, thank you. It's great to be here. Thank you for organising all this. So if I go to the first slide, please. So as you can tell by the colour of my hair and how little of it there is left, that I've been in this business quite a long time, and I'm continually amazed that I haven't yet been found out. But I'm one of those fortunate generation that when I did my PhD as a grad student, I got a rocket. And so I was able to build an instrument and fly it and do the data analysis. So I come from a background where building instruments, using them to get data, analysing the data, and then developing the next generation is a kind of continuous cycle. But I've also been really privileged to be able to benefit from all of these decades of UK-US and US-UK collaborations. So I've been privileged to work on many missions, the most recent of which was James Webb Space Telescope. And I'm now hoping to sort of at least kick off Hab Wells Observatory in the UK. In terms of Leicester's involvement in space research, because I've spent my entire career at Leicester, although I've worked a lot on this side of the Atlantic. We've been doing space for 66 years. Since 1960, we've flown more than 90 missions. And when I last did a count, I was amazed to realize that we actually have 11 instruments currently in space that we've either led or we've made major contributions to. And we've got one more to launch in April. But alongside the space instrumentation, we're experts in optics and sensors. We've also been working much more closely with industry, and we developed something that's pictured on the right-hand side over there called Space Park Leicester, which is a gigantic experiment. We spent 100 million of external funding, not space funding, growth funds and things like that, to bring industry and academia together in a single facility. And then we lock the doors and throw away the keys and see what happens. But if you're ever in the UK, please pay us a visit, because we think it's unique and we think it's going to do great things for the UK space economy. We've got 300 space research people involved in this project. 25 businesses are actually located in that building alongside us. And this works with the Midlands Space Cluster, one of the network of UK space clusters, where we have 300 businesses across the region, Space Park being the anchor facility for all that activity. And then in parallel with that, we have 8 space-active universities in the Midlands, which total around about 1,000 scientists. So it's a great place to collaborate with. Next slide, please. So I've got 3 slides. So the second topic is Hab Worlds. We've heard something about that already, and we talked about it earlier today. And it grows out of this long collaboration the UK has with all kinds of partners. We have had bilateral missions in the past. We have a new bilateral line. And we worked with ESA, and we've also been involved in HST. Most recently, we contributed MIRI to James Webb. We've been involved in the earlier developments of Hab Wells Observatory. Many of us were on panels and working groups, and therefore the UK community is already really well fired up for involvement in Hab Wells. We have a grant from SDFC to support the development of the community. We've run 3 workshops in the past couple of years. A 4th is going to take place in June, but I'll leave Vincent, who's organising that, to tell you a bit more about that in a few minutes. So there's enormous UK science and technical interest, and we've got good academic involvement and lots of potential industry collaborations. So the agency has funded, through its bilateral programme, instrument studies, and we envisage contributing something along the lines of contributing MIRI, but we don't expect to do it alone. We are really interested in collaborations. Although it may be a UK-led programme, we've been working closely with Europe to develop potential collaborations. We haven't really done it on this side of the Atlantic, but we really want to do so. Final slide, please. So, to find these Earth-like planets, you need a really, really big telescope. You can't do it on the cheap. But we've also been very interested in how do you do observatory-class science with small missions. And that's about innovation in optical systems. And we have lightweight X-ray optics. We're about to fly SMILE. So, Harriet, if you could just quickly do the next slide. So this is the SMILE instrument. It's going to image the Earth's aurora from space in X-rays for the first time. Next one, we flick back. Thank you. A mission that I'm particularly keen on is called Sirius, which uses a single grating to focus and disperse light. So it makes the instrument very efficient, but then applying other innovations like a telescope deployment system so we can reduce the focal length, we can put it on an off-the-shelf spacecraft, and we can get a ride share, and we can bring down the cost from about 200 million to about 50 million, about a quarter. So if anybody's interested in this kind of approach, please contact me, and I'm done.
Fantastic. Thank you, Martin. All right. Next up, we have Vincent van Eilen. Over to you. Thank you.
Good afternoon, everyone. It's a pleasure to be here. I'm Vincent van Eilen. I work at the Muller Space Science Laboratory, which is UCL's Department of Space and Climate Physics. Now, if you've ever been to London, you might know UCL and our campus in Bloomsbury, which is in central London. The Department of Space and Climate Physics is not in central London. In fact, we're located in that building over there, which is an hour south of London in the Surrey Hills. It's a fantastic environment. You can see the nature and the area we have around us. If you've never visited, you're all warmly invited here. I'm happy to host you. It's a fantastic place. There's about 200 of us working in that department, scientists and engineers who have worked on a wide variety of missions. And I asked Harriet, and she said, don't worry, you can talk about all of them. There is plenty of time in this lightning slot. So I'll start with the first. That's a joke. I just had to highlight just one of them. And so, of course, the one I want to pick, I'm an exoplanet astronomer, is Habitable Worlds Observatory. Right. And exoplanet science is an incredibly exciting field. It's still a very young field. It's a field that dates back only to 1995 with the discovery of the first exoplanet, only back in 1995. Since then, we have discovered thousands of exoplanets. It's a growing field. We know increasingly more about these planets, as well as just finding them. We're starting to characterize them. But the real next frontier is really what Habitable Worlds Observatory can hope to offer us, which is to study the properties of these exoplanets in great detail, to really look at the atmosphere, not just of any planet, but of those kind of planets that might actually have life, that have the right temperatures, that might have liquid water, and that could have life. And it's just an incredibly exciting prospect, and we heard a little bit about it earlier today. It's quite hard to unambiguously identify what life really is and how we will find it. But it is nevertheless incredibly exciting. Last summer, I was in Washington, D.C. at the Hub Worlds conference there. And if you were there, you would have come away thinking, we are going to do this. And that's, for me, what's defined lots of this partnership with the US, that just inspirational kind of can-do attitude where we can do these kind of things. Habitable Worlds has been identified as a priority for the US as the top of the decadal survey. And in the UK, there's been very much the same kind of excitement. We have started bringing people together. We've started doing things, and including the UK Space Agency has started funding some of our teams. And what you're seeing here is a team funded by UKSA that I'm leading with colleagues from across different UK universities at a concurrent design facility in Portsmouth just last week, where we were studying the prospect of a high-resolution imager and all it could do for exoplanets, but also many other kinds of science. Solar system science, planetary science, things like planetary defense, and so on. Right. And so the UK people are really excited. We have our own version of the decadal survey. Here's a white paper that I wrote together with my colleague Richard Massey there, and co-signatures, about 150 of them from across the UK and many European places. The process is still running, but based on the excitement we're seeing, I'm pretty confident it will also rise to the top of our UK priorities over the next months. Next slide, please. Now, I couldn't talk about all the missions, but I just wanted to quickly highlight. Here is a kind of list of the kind of things we've been doing at MSSL in many ways over the last couple decades. I just want to pick out here James Webb near-spec calibration units, the leadership on the VIS instrument of Euclid, and recently a lot of work on the Plato CCDs. But you see a list of missions there, many of which have been mentioned here already today, ranging from Cassini, things like Solar Orbiter, ExoMars, Rosalind Franklin, which is right on there, and many other really exciting missions. So I won't talk about them, but we've had many roles in many of these different missions, sometimes small, but in many cases also very significant roles. So if you're interested in any of those, happy to talk to you, and thank you very much.
Thank you, Vincent. All right. Fantastic. All right, next up we have Ravi Desai. Over to you. Thank you.
I've got the slides. Okay, that's fine. Hello, everybody. So today I'm firstly going to talk about an existing collaboration effort with the US. And this is a mission concept we're proposing to the European Space Agency called RAWS, Research Observatory for Atmospheric Responses to Sun Magnetosphere Interactions. We have two main science questions on the top left, which you can see. We want to measure how much energy and momentum is transported into the upper atmosphere. And the second question is we want to understand how this energy and momentum is redistributed within the ionosphere thermosphere system. To achieve this, we're proposing 4 identical microsatellites, which will be in a polar descending orbit. And we have this novel orbital concept, you can see in the top middle, where we have opposing arguments of perigee. So we maintain orbital periodicities, we sample different altitudes, and we obtain a tetrahedron at higher over the North Pole and the South Pole to measure the curl of the magnetic field, which gives you the current and the energy flowing into the upper atmosphere. Now, we have a wide consortium, which includes US scientists. We've heard about the advances that can be made when we're all working together. Our mission has progressed through an ESA Phase 0 study and also through a University of Portsmouth CDF study. And I understand the CDF was actually developed through the UK-US bilateral program. So there's another example of collaboration. We've now been shortlisted for Stage 2 within the ESA FAST mission. And on the right, you can see a list of payloads, which I won't go through all of them in detail, but I'll highlight one from UCLA, the energetic particle instrument, where we're proposing this US contribution to this mission. I'll also briefly mention we've got these magnetometers, this dual sensor concept, where we have a conventional vector fluxgate magnetometer and a quantum scalar magnetometer to provide an absolute reference frame. So this allows me to segue into the second topic, which I'm going to talk today. If we can go to the next slide. At the University of Warwick, we're developing these nitrogen vacancy in diamond magnetometers. So on the top left is a basic illustration of how they work. We shine green laser light in. We modulate the spin of the electrons, and that modulates the red light. The photoluminescence comes out. So through this optically detected magnetic resonance, we can measure the magnetic field, the absolute magnetic field, as the function of fundamental physical constants along the 4 NV axis. So this uniquely provides an absolute vector magnetometer. So we have a really strong NV research at Warwick. You can see on the bottom left, we build the world's most sensitive fiber-coupled diamond magnetometers, so far reaching 30 picotesla per hertz, which is still advancing and still becoming more sensitive. So these magnetometers are great for future missions. They have a very large dynamic range. So this means that if you're in a high Earth or planetary field, you have the same principle, the same mode of operation as if you were in a very low field, such as an outer solar system or even in the interstellar medium. We're temperature insensitive, it's solid state, it's rugged, and it's radiation hard. And as I mentioned before, it's fiber coupled, so we can have these very small lightweight sensor heads on the end of a boom, which through fiber coupling, we put the main electronics on the main spacecraft. On the right, you can see some early results there where we're detecting the 4 orientations on the top right of the NV. And on the bottom right, you can see a power spectrum, which is where you see this fantastic flat power spectrum from down to less than a hertz out to several hundred and even thousands of hertz. So if we move to the next slide, another quantum technology we're developing at the University of Warwick is based on the field of optomechanics. So within this field of optomechanics, it's quite different from maybe space science. We use lasers to trap these nanoparticles. And people do this to study the quantum nature of the macro world. So typically you would meticulously isolate this experiment and you would try and see, does a nanoparticle have a wave-particle duality? Is the quantum world manifesting in the real world? Within this scenario, what we're doing is we're actually exposing this nanoparticle to the ambient RAM pointing direction of the spacecraft. And this means we can use this fantastic capability and technology developed within this field of optomechanics, where we can measure the motion of this particle to really high precision. And this means maybe you can even see it in the top left there. You can see that if you have an individual kick from an incident particle, we are measuring this kick, and we can therefore infer through the momentum recoil what this particle is. So this is a brand new sensor concept, essentially with 100% detective efficiency. And this can uniquely actually access a very wide variety of momentum space. You could be in the upper atmosphere, in the thermosphere, detecting neutrals or charged particles, or you could actually be looking at interstellar neutrals or energetic neutral atoms, and you essentially have this single particle which is sensitive to the ambient environment. We've developed the concept through UKSA and ESA funding, and we have a preprint on the archive as well. But thank you very much for letting me talk.
Fantastic. Thank you, Ravi. All right, next up we have Christophe Dumas. Over to you. Thank you.
All right, thank you for the invitation. So I'm Christophe Dumas from ATC. Also an example of collaboration between UK and US, because I actually spent quite a few years working between Caltech and JPL before I joined ATC. Okay, so for those of you who don't know what ATC is, it's one of the STFC lab in the UK. I would say it's probably the only one that's fully dedicated to astronomy in terms of developing instrumentation for astronomy for both ground and space-based astronomy projects. We work very closely with RAL Space as well, which is one of the other labs. Paul Eccleston is representing RAL Space here, is here with us in the group. About 130 people working on these projects, more than 30 projects, as I said, space and ground-based projects. Why do I say ground? Also because some of these ground-based projects are also involving UK-US collaboration, okay? So just an example of those, okay, you don't have to know all the acronyms, but Harmony for the ESO ELT, the ELT is going to be the largest telescope ever built. It's going to be transformational, like Palomar was at the time it was built 70 years ago. And Harmony is also collaboration between many, obviously, partners, but the UK and the US are involved. And we are actually leading the construction of these instruments from ATC. In terms of space, you're going to see in the next slide that we were involved in JWST with the MIRI instruments. We're also involved with LISA. Also, UK and US are involved in LISA. LISA is an interferometer for gravitational wave detection from space. 3 spacecraft flying in formation at N2, and ATC is actually building all the core of the optical benches for 3 of the spacecraft that are going to fly sometime in 2035. Next slide, please. All right, so I said JWST, you already saw this from my previous speakers. The UK ATC was, I said was because it's flying now, okay, the place where the coordination for MIRI was actually managed by my predecessor at ATC before I joined. But ATC was also involved in doing quite a few things, leading the instrument design for MIRI, as well as leading all the performance verification, leading the design and the development of the pre-optics for the spectrometer of MIRI, also the instrument simulator and the data pipeline for these instruments. Okay, you see one of the science highlight, very recent from last year, a paper published on exoplanets, recovering all the planets from the system HR 8799, 4 of them, and measuring for very precisely the radiation coming from this planet that allows us to actually refine our knowledge of their diameter, but also the atmospheric models on some of these exoplanets. Also, the first resolved detection, Spitzer detected a debris disk already for this system, but that was the first resolved image of the warm debris disk in this system, obtained at 1.5 and 2 microns. That's the 2 last images that you see on the right. Okay. Next slide, please. Okay, so this slide is about future projects. You understood that the UK is very much interested in supporting and getting involved in the Habitable World Observatory. From the JWST MIRI experience that was very successful, we basically want to build a sort of relationship based on this model as well that works very well. ATC is involved in supporting the 2 mission concept studies that were already described by Martin and Vincent. We're providing system engineering, project management, optical and mechanical design for these early studies. We're also leading some optical design studies for the near-infrared IFS, infrared field spectrograph that's going to go behind the coronagraph. And we have one of our students who was actually going to spend 3 months of internship at JPL this summer. Another field that we are trying to get involved in is ocean worlds, astrobiology. I'm a solar system scientist myself. And we are responding to an ESA M8 mission concept to send a spacecraft, an orbiter, and a lander on Ceres, which is a water world itself. We believe that it contains a huge amount of liquid water below the surface of Ceres, and we want to understand how this water is distributed. So we are going to send a spacecraft, if the mission is selected, And ATC will actually build the hyperspectral imager for Calico, which is the name of this mission. This is very much like a pathfinder for, also you heard, Enceladus mission to another ocean world around Saturn. That's it. Thank you.
Fantastic. Thank you very much, Christoph. All right, next up we have Annika Patel from Caltech. Thank you, Annika.
Hi everyone, I'm Annika, I'm a physics PhD student at Caltech, and today I'm going to be briefly talking about the cosmic microwave background experiments, also known as CMB experiments. We know that science has always progressed through collaboration, and the partnership between the UK and the USA has been especially progressive when it comes to space science and astrophysics. And a concrete example of this collaboration is CMB experiments. So the plot here behind me shows the timeline of the universe, starting from the Big Bang at the very beginning to 13.8 billion years later to the universe that we see today. And what we would really like to understand is what happened at the very start of cosmic history. And so the only way that we're able to look at this is observing the cosmic microwave background radiation. And this is when the universe first became transparent around 380,000 years after the Big Bang. There are tiny structures and patterns within this radiation which carry information about physics from much earlier times of the universe. So by probing the CMB, we can indirectly look at the very first moments of cosmic time. From the very start, the CMB experiment has been a deeply collaborative field. It brings together scientists, engineers, and institutions globally, and the UK and the USA collaborations have played a particularly productive role. The next slide here shows a couple of ground-based telescopes operating to probe the CMB. So examples mostly are from Chile and the South Pole, and some main examples are Bicep Array and Simons Observatory, and they remain essential for probing the CMB. They have ground-based telescopes, offer rapid deployment, iterative improvements, and in the future will complement space missions by testing instruments, methods, and analysis. So I'm fortunate enough to work on the Bicep Array experiment located down at the South Pole. And at Caltech, we mostly work on design and integration of our detectors and often have our students deploy down to the South Pole, which is very exciting. And this is, yet again, this experiment is another example of collaboration. We have institutions from the UK, USA, and Canada probing the CMB, and actually our filters come from Cardiff University. On the next slide, on the left, you can see some heritage spacecraft. So that's WMAP and Planck there. And these previous space-based CMB missions laid the foundation for precision cosmology. So WMAP was a NASA mission that mapped the CMB across the full sky, and it mapped it with unprecedented accuracy in the early 2000s. And its successor was Planck, which was a European Space Agency mission heavily supported by NASA, and that produced the most detailed CMB map yet to date. On the right here, we have future CMB missions. So the Lightbird mission is a Japan-led spacecraft. It will aim to probe the CMB with contributions globally, but also from the US and UK, and again shows how global partnership can advance instrumentation and analysis. PICO at the very bottom there is a mission concept. It stands for Probing Inflation and Cosmic Origins, and it represents the next international step on CMB research. It builds on Lightbird's model of targeting even higher sensitivity measurements of CMB, and it will probe inflation, early universe, and neutrino masses. So space-based missions such as PICO have been crucial because they can observe the full sky with ultra-low systematics, and we're able to access frequency bands that otherwise we couldn't access because they'd be blocked by Earth's atmosphere. So by bringing together this expertise from the UK and the USA and worldwide institutions, it exemplifies how international collaboration can drive cutting-edge cosmology. On a personal note, I come from the UK, but I did my undergrad and I'm now pursuing my PhD in the States. And through this journey, I feel like I've quickly learned the importance of international collaboration and how it's essential to driving scientific discovery. And I feel like it's through these global partnerships, as many people have already said today, that we're able to accelerate our work. And I'm very excited to be part of this future. So thank you.
Fantastic. Thank you so much, Annika. All right, next up we have Matthew Cosby. Thank you.
Hello, everyone. What I'm going to do is I'm going to try and get as many highlights of UK and US engagements. So Goonhilly, which is a station in UK, has a long history. We've In 1962, we were part of the first transatlantic TV pictures to come across the pond. A few years later, in 1969, we distributed the pictures of Neil Armstrong in Apollo 11, and in 1977, we were the first international nodes on the internet. This was all done through the GPO, or the British Telecom, and British Telecom decided to sell the site in 2014, and it was bought by a small private company, which we've then established to do deep space and commercial communications. Next slide, please. We've increased our collaboration by buying a US company. We have 2 teleports in the US, one on the east coast and one on the west coast, just an hour and a bit up the coast from here. But it's the station in Goonhilly, which is in the most southerly point of the UK's mainland, is what I want to talk about now. We have a 32-metre antenna, which we've upgraded, and we got operational in 2021. This has become possible through the international collaboration that was actually founded by JPL Caltech in the 1980s by an expat Brit in the 1980s, CCSDS, and we've managed to create this antenna based around these protocols that allows us to talk to all the missions that have been put up there from the institutions, whether it's ESA, whether it's JAXA, and whether it's NASA. And we're using this as a way of basing this as a commercial model to offering data downloads in a private industry. Next slide, please. So this is why I got invited here. We were part in February 2024 as the first soft landing of an American spacecraft since Apollo 17. We were the prime station. The dish I was talking to you about earlier was the prime station for the landing. Unfortunately, the lander had a suboptimum landing. It's a bit diplomatic, because I know we've been filmed. And so the actual comms was reflecting off the lunar surface, so we had to do a slight modification on the dish pointing to get it off the moon to lower the noise floor to actually get the signal back. And what a great show of US-UK collaboration by having the dish, which is currently on picture here, which was projected into Times Square when Intuitive machines were being listed on the NASDAQ. So we think that we can create a private deep space network. We're working alongside European Space Agency's network. We're working alongside JPL. We're in fact designated a DSS 59 as part of the deep space network. So answering your earlier question about how we work together is that we don't do it in isolation. We do it together, and then we learn from each other's mistakes and then drive it forward so we can actually help each other. So what our business model is to try and take on all the missions that you've currently got flying, so that NASA and ESA can concentrate on the more complicated missions, and so that frees up the deep space, the institutional deep space networks to be able to do the more complicated things. Just to demonstrate what we're doing going forward, the dish is also being configured to work with IMAP. We did that today, and as Neil has already mentioned, we did some work with Lunar Trailblazers. We configured both antennas that we have on site to try and identify and try and find the mission. But I encourage you to, in the networking, is to get together, come out with more complex instruments with more data, so we can download it for you. Thank you.
Thank you, Matt. All right, fantastic. So I just want to ask one more round of applause for all our fantastic lightning talk speakers today. We have covered a lot of topics, and we have not had time for questions. So I really encourage you, if someone has inspired an idea, a potential collaboration, something you want to talk more about, please do that in the reception. It is now just me between you and our wonderful drinks that we have over in the Keck Center courtyard. So I'm going to be very brief. I want to say a huge thank you to everyone who has been here today. But before we go, I want to have the opportunity to tell you a little bit more about the Keck Institute for Space Studies. So before I do that, I want a quick show of hands. Could you raise your hand if you've been involved in a KISS study in the past? All right, we got some friendly faces in the audience. Fantastic. So if you haven't heard of KISS and you've still got questions, please do come see me in the reception, or please do ask one of the colleagues that we've got who have just raised hands here. We are a think and do tank that is based here at Caltech, and we ignite breakthrough ideas that aim to shape the future of space exploration, science, and technology. We're looking to develop those ideas and concepts that can revolutionize space exploration in the future. Fostering collaboration is really key to what we do. So we're so glad to be able to partner with our colleagues at the British Consulate to organize these kind of events, to bring together experts from different areas, different perspectives, and different backgrounds to help drive these ideas forward and make them happen. We're also really passionate about empowering the future leaders of the space industry and the space community, and it's been wonderful to hear about some of the research of our early career professionals in this event as well. We are looking to catalyze innovation and make the impossible possible. We select a number of thematic topics each year where we're looking at what are those crazy ideas that could revolutionize how we do space exploration going forward. And we're always looking for new ideas. We have an annual call that goes out to solicit proposals. We have a track record since 2008 when our institute was founded. We organize workshops, events to really convene world-leading experts from organizations and from countries around the world to develop those ideas that have real-world impact. Our current portfolio tackles the most forward-looking questions in science exploration, science and technology. And in recent studies, we've been really privileged to welcome colleagues from the UK from a number of different research institutions. We very much hope that that continues as well. So if there are ideas that spark here, topics that you think warrant further discussion, idea and development, please do see if the Keck Institute for Space Studies could be a home to take those ideas forward. As an institute, we are looking at developing those ideas through our study programs. Again, please do ask me about that if you're interested. We're here to build community through events, and we're so honored to be partnering with the British Consulate to support that today. We also have a public lecture series, and we inspire future space leaders through our affiliate program, one of which is Annika, so shout out to Annika for her fantastic presentation earlier. I will stop there. That just leaves me to invite you to join us for our evening reception, which is over at the Keck Center courtyard for the next hour. We'll have drinks and refreshments. Very much hope that the conversations that we've had this afternoon will spark conversation, I'm sure, for much more than an hour, but at least we'll be getting things started. You can find the Keck Center courtyard if you go out of here and you just take a left. You should be able to follow the signs to see my colleagues who are there to welcome you. Again, before we depart, I just want to extend a huge thanks to everyone here, but in particular to the organizers, the British Consulate General in Los Angeles, particularly to Arinya and the fantastic team that we've had the pleasure of working with, to our colleagues at the UK Space Agency, Caltech and JPL, and everyone who has taken the time to be here. I hope there are many more collaborations between the US and the UK to come. Thank you very much and enjoy the rest of the evening. Thank you.